1 light year sounds like a measurement. It is not. It is a threshold, one that rewrites your biology, bends your experience of time, and strips away everything familiar about reality. And the deeper you go into that journey, the stranger it gets. At what point during that journey do you stop being a traveler and start being something else entirely? If you want to keep seeing the universe in ways that genuinely shift your perspective, make sure to give this video a like. Now let's get started. 1 light year. That phrase gets tossed around constantly, but almost nobody takes a moment to truly feel what it represents. 9.46 trillion kilometers. If you lined up every single human being who has ever lived, all 108 billion of us, stretched end to end, you would still need to repeat that line more than 12,000 times just to cover the distance of a single light year. That is not just a large number. That is a fundamentally different category of reality than anything your nervous system was designed to process. But here is what makes this journey truly fascinating, and what most people never stop to think about. It is not just the distance, it is what the distance does to your body, to your perception, to time itself, because the universe does not follow the same rules out there. The deeper you go into interstellar space, the more the cosmos reveals just how strange and layered its laws actually are. And the science behind those changes is some of the most astonishing material ever uncovered by human curiosity. Let's start somewhere most people never begin. What is actually out there between here and 1 light year away? Most people picture space as this clean, empty void, a black canvas with stars painted on it and nothing in between. But that image is wrong. Interstellar space, the space between star systems, is filled with something scientists call the interstellar medium. It is a complex, living mixture of gas, mostly hydrogen and helium, along with microscopic dust particles, plasma, magnetic fields threading through the dark like invisible rivers, and a relentless rain of high-energy particles known as cosmic rays. It is not crowded. We are talking about sometimes just 1 single atom per cubic centimeter, but over 9.46 trillion kilometers. Even that adds up to something real, something that matters, something your body would have to reckon with. And here is where things get genuinely wild. Those cosmic rays are not gentle visitors. Cosmic rays are atomic nuclei, mostly protons, that have been accelerated to extraordinary energies by some of the most violent events in the universe, supernova explosions, the crushing gravity around neutron stars, and the titanic jets launched by supermassive black holes at the hearts of distant galaxies. Some of these particles reach energies so extreme that physicists gave them a name all their own: ultra-high energy cosmic rays. And a single one of those particles can carry kinetic energy comparable to a well-thrown baseball. Think about that. 1 subatomic particle, invisible to the naked eye, hitting with the force of a baseball pitch. In interstellar space, you are exposed to a constant stream of these with absolutely nothing to protect you. This is one of the first serious, unavoidable challenges of your journey. Radiation. Not the sunburn kind, the deep, penetrating DNA-shredding kind. Studies built on data from NASA's Curiosity rover, which carefully measured radiation levels during its cruise through interplanetary space on the way to Mars, showed that a human being traveling without adequate shielding would receive a dose of roughly 1.8 millisieverts of radiation per day. And that is still within our solar system, where the sun's enormous magnetic bubble still offers a measure of protection. Once you cross beyond the heliosphere, that bubble extends out to roughly 100 to 120 astronomical units from the sun. You leave that protection entirely behind. And 1 light year is 63,000 astronomical units. For the overwhelming, crushing majority of your journey, you are fully exposed to the raw, unfiltered cosmos. The heliosphere itself deserves a moment of appreciation because it is remarkable. It is this vast, comet-shaped structure of charged particles and magnetic energy that our sun breathes out in every direction. It acts as our cosmic shield, deflecting a significant portion of galactic cosmic rays before they ever reach Earth. We live inside it without ever thinking about it, the way a fish doesn't think about water. But the moment your journey carries you beyond it, and that happens astonishingly early in the context of a 1-light-year trip, you step outside the only shelter our star has ever given us. If the idea of traveling between stars already feels staggering to you, I want to point you towards something this video on the card above. We explore why even warp drive would not save us from the distance between the stars. It tackles something most science fiction completely glosses over. Even our most imaginative propulsion ideas still run headfirst into the brutal math of interstellar distance. That video and this one are a natural pair. The link is in the description and pinned on the comments. Now back to what you would be moving through. Because the interstellar medium is far more layered than most people realize, thundering through all that gas and dust are interstellar magnetic fields. These are not small local features. They stretch across hundreds of light years, woven into the structure of the Milky Way, like a nervous system threading through a body. Astronomers have mapped these fields using a technique called Faraday rotation. They observe how the polarization of radio waves from distant pulsars gets twisted as it travels through magnetized gas. What they found revealed that the galaxy is laced with these magnetic rivers, and they are deeply connected to how star-forming clouds collapse, how cosmic rays travel, and how the galaxy itself evolves over billions of years. And here is something that I want you to sit with for a moment, because it is one of those facts that changes the way you see yourself. The atoms in that interstellar gas, the hydrogen, the carbon, the oxygen drifting through the dark between stars. Many of them were forged inside ancient stars that exploded long before our sun was born. When a massive star reaches the end of its life and detonates as a supernova, it blasts its outer layers, rich with carbon, oxygen, nitrogen, silicon, and iron, out into the surrounding space. That material drifts for millions of years through the interstellar medium. Eventually, gravity gathers it into new clouds. Those clouds collapse into new stars, new planets, new chemistry, new life. The atoms in your body, the carbon in your cells, the oxygen in your blood, the iron at the heart of every hemoglobin molecule, they took that journey. They were part of the interstellar medium. They drifted in that darkness. You are not traveling through foreign territory. In the deepest sense possible, you are traveling through the stuff you are made of. You are returning to your origin. But here is where the journey takes a turn that will completely reframe everything you think you know about time, about distance, and about what it even means to be you. Because when you start moving fast enough, and I mean genuinely fast, a significant fraction of the speed a photon travels, time itself stops behaving the way it does in your living room, or your kitchen, or anywhere on Earth. Time becomes elastic, it stretches. And what that means for a journey of 1 light year is something so counterintuitive, so genuinely strange, that even the physicists working with Einstein in the early 20th century had to wrestle with accepting it as real. Now, we are going to get deep into exactly what happens to time during this journey, what you would experience, what people back on Earth would experience, and why those two things are completely, irreconcilably different. The answer might just shift the way you see your entire life. So let's talk about time. And I don't mean time in the casual, everyday sense, the kind you track with a watch or feel dragging on a slow afternoon. I mean time as a physical dimension of the universe, something that bends, something that stretches, something that the cosmos treats with a flexibility that our human intuition is simply not wired to grasp naturally. Because once you start moving at a meaningful fraction of the speed light travels, Time stops being the universal constant we were all raised to assume it was. This is not science fiction. This is not a thought experiment cooked up by someone with too much coffee and too much imagination. This is one of the most rigorously tested, most experimentally confirmed ideas in all of physics. It is called time dilation, and it falls directly out of Albert Einstein's special theory of relativity, published in 1905. More than a century later, we have confirmed it with atomic clocks on airplanes, with GPS satellites that require constant relativistic corrections to give you accurate directions, and with particle accelerators where subatomic particles live far longer than they should because they are moving so fast that their internal clocks are running slow. The universe does this. It is real. And on a journey of 1 light year, it becomes the defining feature of your experience. Here is the core idea, as simply as it can be put. The faster you move through space, the slower you move through time, relative to someone who is standing still, not metaphorically, not as a perception trick. Actually, physically measurably slower. Your heartbeat slows relative to theirs. Your cells age more slowly relative to theirs. Your thoughts, your memories, your entire biological existence unfolds at a reduced rate compared to the world you left behind. And the closer your speed gets to the speed light travels, the more extreme this effect becomes. Let's make this concrete. Say your spacecraft, and for the purpose of exploring the physics, let's imagine a vessel capable of sustained acceleration reaches 90% of the speed light travels. At that velocity, the time dilation factor, which physicists call the Lorentz factor, works out to roughly 2.3. What that means in practice is that for every 2.3 years that pass back on Earth, only 1 year passes for you. You age more slowly than everyone you left behind. You step off your ship after what feels to you like a year, and the people waiting for you have aged 2.3 years. Push your speed to 99% of the speed light travels, and that factor jumps to roughly 7. At 99.9%, it reaches about 22, and at 99.99%, closer still, it climbs past 200. So here is the extraordinary implication. A journey of 1 light year, which would take just over a year of travel time at nearly the maximum possible speed, might feel to you like only a few weeks, or even less, depending on how close to that ultimate speed you get. You leave Earth, you travel, you arrive. You have aged perhaps a few months. Earth, meanwhile, has aged over a year. The gap between your time and theirs is real, physical, and permanent. There is no catching up, there is no undo button. Time moved differently for you, and when you return, the universe has already written that difference into its ledger. Now, this raises something that most science communicators rush past. But I want to stay with it for a moment, because it is one of the most philosophically stunning corners of modern physics. What does it actually mean for time to pass differently for two different observers? It means that there is no single universal now. The idea that there is one shared present moment, one tick of the cosmic clock that applies to everyone, everywhere, is simply not how the universe works. Einstein replaced that intuition with something called the relativity of simultaneity. Two events that appear to happen at the same time for one observer can appear to happen at different times for another observer moving at a different speed. Now is personal, now is local, now is relative. This is deeply strange. It should feel strange. If it feels comfortable and obvious, it probably means the weight of it hasn't fully landed yet, because what it implies is that the universe doesn't have a single timeline running through it like a spine. It has a fabric, what physicists call space-time, and every object moving through that fabric carves its own path, its own personal timeline called a world line. Your world line through space-time is uniquely yours. No one else in the universe has the same one. And the faster you move through space, the more your world line tilts, and the slower you move through time. But let's bring this back to the practical reality of your journey. Because as beautiful as the physics is, the engineering consequences are brutal. In order to experience meaningful time dilation, the kind where your clock runs noticeably slower than Earth's, you need to be moving at a very large fraction of the speed light travels. And accelerating any object with mass to those speeds requires energy, an almost incomprehensible amount of energy. Let's think about it this way. To accelerate a spacecraft carrying a single human being, let's say the ship has a total mass of about 100,000 kilograms, which is actually quite modest by any realistic spacecraft standard. To 90% of the speed light travels, the kinetic energy involved is staggering. We are talking about something in the range of 10 to the power of 22 joules. For comparison, the entire world's annual energy consumption is currently somewhere around 6 times 10 to the power of 20 joules. So you would need roughly 1,600 years worth of global energy output just to push that modestly sized ship to 90% of light speed. And that assumes 100% efficiency, no heat loss, no waste, no inefficiency of any kind. No real-world propulsion system comes close to that. This is one of the central walls that the universe builds between us and the stars. And it is a wall made not of ignorance or lack of technology, it is made of physics itself. The laws of nature place a kind of tax on speed, and that tax grows exponentially the faster you go. Every incremental increase in speed demands exponentially more energy. You can never actually reach the speed light travels, only approach it asymptotically, spending more and more energy for smaller and smaller gains in velocity. The universe is telling you something here. It is not cruel, it is honest. The cosmos has rules, and those rules have consequences. Now here is something that opens a completely different dimension of this conversation, and it connects to one of the most active frontiers of research in physics today. What if there were a way to sidestep this energy problem entirely? What if, instead of accelerating yourself through space, you could somehow manipulate the space around you? This is the idea behind what physicists call an Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. The concept is genuinely fascinating. Rather than moving through space in the conventional sense, a hypothetical vessel would sit inside a bubble of flat space-time, while the space in front of it contracts and the space behind it expands. The ship itself never locally exceeds the speed of light. It just rides a wave of warped space-time, the way a surfer rides a wave. In theory, this could allow travel across vast distances without the time dilation penalty or the catastrophic energy requirements of conventional acceleration. The problem, and there are several serious ones, is that the original Alcubierre solution required exotic matter with negative energy density, not antimatter. Something stranger, something that may not exist in any form accessible to us. And even if we set that aside, more recent analyses have shown that the bubble itself would likely accumulate high-energy particles at its front wall during travel, releasing them in a devastating burst upon deceleration, essentially turning your arrival into a catastrophic energy event. The universe again finds clever ways to protect its speed limits. But here is why this still matters, and why physicists still study it. Science does not advance by only exploring what is currently possible. It advances by carefully mapping the boundary between possible and impossible, because sometimes what looks like an impossible wall turns out to be a door that simply hasn't been opened yet. Alcubierre's idea forced physicists to take seriously the question of whether space-time geometry itself could be engineered. And that question, even if the current answer is not with any known physics, is still worth asking, because the history of science is full of ideas that were once considered pure fantasy and are now engineering reality. Let's come back to your body. because all of this physics, as exhilarating as it is, exists in parallel with a biological story that is just as profound and far more visceral. You are not a photon, you are not a particle in an accelerator. You are a system of roughly 37 trillion cells, each one carrying out thousands of biochemical reactions per second, each one exquisitely calibrated for the conditions of life on Earth. And interstellar space is nothing like Earth. We talked about radiation, but there is another biological challenge that is just as serious and far less discussed. It is called muscle atrophy and bone density loss, and in the microgravity environment of a spacecraft in deep space, it begins almost immediately. Studies from the International Space Station, where astronauts spend typically 6 months at a time in microgravity, show that without rigorous daily exercise protocols, we're talking 2 hours every single day on specialized resistance machines, astronauts lose roughly 1 to 2% of bone density per month. Their muscles weaken, their cardiovascular system becomes less efficient, their sense of balance is disrupted, their fluid distribution shifts toward the upper body, creating chronic head pressure and affecting vision. And those effects are documented at the International Space Station, which is still relatively close to Earth, still receives some gravitational influence, and still allows for resupply and medical support. On a journey to 1 light year, you are completely on your own, no resupply, no emergency evacuation, no rescue mission. Whatever your ship carries, and whatever your body can endure, is all you have. And the journey, even at the most optimistic conceivable speeds with technologies we don't yet possess, would last years, possibly decades, of subjective time. There is something I want you to feel here, not just understand, because we are not just talking about engineering problems or medical challenges. We are talking about what it means to be a human being in the universe. Right now, as you are watching this, you are moving through space at an extraordinary speed. The Earth orbits the Sun at about 30 kilometers per second. The Sun orbits the center of the Milky Way at about 220 kilometers per second, and the entire Milky Way is moving through the cosmos at speeds that dwarf both of those. You have never been still, you have never been stationary, you have always been a traveler. But your body was built for a very specific slice of this motion. It was built for a planet, for gravity, for a magnetic field wrapping around you like a protective cocoon, for a thin blanket of atmosphere filtering the worst of the sun's energy before it reaches you. Take all of that away, and you are fragile in ways that are almost poetic in their honesty. You are a creature of Earth, and space reminds you of that every single moment. There is a moment that every astronaut who has ever looked back at Earth from orbit describes in almost identical terms. It does not matter where they are from, what language they speak, what beliefs they hold, or what kind of person they were before they left the ground. The moment they see Earth, small, luminous, impossibly fragile against the black, something shifts inside them permanently. Psychologists and neuroscientists have studied this phenomenon so extensively that it now has its own name, the overview effect. It is a cognitive and emotional transformation triggered by the sudden, visceral realization of how small and precious and isolated our world truly is. Now imagine something orders of magnitude more extreme. Imagine looking back not from a few hundred kilometers above Earth's surface, the altitude of the International Space Station, but from 1 light year away, 63,000 astronomical units. At that distance, the sun would not be a disk. It would not be a warm golden presence dominating the sky. It would be a point, a single pale unremarkable dot, indistinguishable to your naked eye from thousands of other stars scattered across the darkness. Our entire solar system, every planet, every moon, every asteroid, every comet, every spacecraft humanity has ever launched would be compressed into that one tiny point of light. And there is a very real possibility that you would not even be able to find it without help. This is not a poetic exaggeration, this is geometry. The apparent brightness of a light source falls off with the square of the distance. At 1 light-year, the sun would shine at an apparent magnitude of roughly 0.4, which actually still sounds bright, but here is the catch. From that distance, you would be looking at the sun from outside the plane of the ecliptic, surrounded by the full darkness of interstellar space, with no atmosphere softening your view, no scattered light filling the sky with blue. Every star in the galaxy would be visible at once with perfect clarity. The sun would be one among thousands of comparably bright stars, with nothing to mark it as special, nothing to tell your eyes or your heart that everything you have ever loved exists in that direction. The psychological implications of this are profound. And I want to be careful here, because this is an area where science and human experience meet in a way that deserves genuine respect and attention. NASA has invested heavily in understanding the psychological risks of long-duration spaceflight, and what they have learned is sobering in the best possible way. It reveals just how deeply our minds are shaped by the world that built us. One of the most significant psychological challenges of deep space travel is something researchers call Earth out of view phenomenon. It describes the cognitive and emotional disruption that astronauts may experience once Earth is no longer visible, no longer a reference point, no longer a comfort, no longer even a speck of blue in the window. Studies using analog environments, isolated Antarctic stations, submarine deployments, the Mars Desert Research Station in Utah, show that human beings cut off from familiar environmental cues experience measurable changes in mood, cognition, and social behavior. Sleep patterns shift. Decision-making becomes more conservative, sometimes to a fault. A phenomenon called third quarter effect, a dip in morale and productivity, roughly 3/4 of the way through a long isolated mission, appears consistently across virtually every analog study ever conducted. And those analog environments still have Earth, still have a sky, still have seasons and wind and the smell of soil. On a vessel traveling through interstellar space, the isolation is of a different order entirely. You are not cut off from civilization, you are cut off from the planet, from the ecosystem, from the gravitational, electromagnetic, and biological web that your nervous system evolved within over 4 billion years of life on this world. You would be, in the most literal sense possible, the most isolated human being who had ever existed. And yet, and this is where the human story becomes something genuinely beautiful, history suggests that some people can not only survive that isolation, but find within it something transformative. The accounts of solo sailors crossing vast oceans, of explorers wintering in polar darkness, of monks spending years in remote silence. They speak again and again of a kind of clarity that only comes when all the noise is stripped away, when there is nothing between you and the universe but your own mind. Space, at those distances, might do something similar, strip away everything surface level, leave only what is essential, leave only the questions that matter. But let's talk about something that most discussions of interstellar travel completely ignore, and it is one of the most practically terrifying aspects of the whole journey. Communication, specifically the slow, agonizing collapse of your connection to everyone and everything you left behind. Right now, signals travel at the speed light moves. That is the universal speed limit for information. Nothing, no radio wave, no laser pulse, no quantum entanglement trick can carry information faster than that, and at 1 light year, the consequence is inescapable. Any message you send back to Earth takes 1 year to arrive. Any response takes another year to return. A simple conversation, the kind you might have with a friend over a cup of coffee in a few minutes, would take a minimum of 2 years round trip. 2 years between question and answer. 2 years of waiting to find out if your message was even received. Think about what that means emotionally. You cannot call home. You cannot check in. You cannot receive news from Earth in any meaningful, timely sense. By the time any message reaches you, everything it describes is already over a year in the past. The world you left behind is perpetually 1 year older than any information you receive. People you love age and change and live their lives in a present you can never access. You exist in a kind of temporal isolation that goes beyond physical distance. You are separated not just by space, but by the structure of reality itself. NASA researchers studying long-duration mission communication, even for a Mars mission, where light travel time reaches up to about 22 minutes one way, describe the transition from real-time communication to delayed communication as one of the most psychologically significant thresholds a crew can cross. At 22 minutes, you lose the ability to have a live conversation. At 1 year, you lose the ability to have any meaningful dialogue at all. What remains is correspondence, dispatches from across an abyss. Letters that arrive after the season has already changed. Now, I want to zoom out from the human drama for a moment and look at something that I think is one of the most beautiful scientific facts connected to this journey. 1 light year out, you would be in a completely unique position to study the sun itself, in a way that no instrument on Earth or in orbit has ever been able to. Here is why. There is a phenomenon predicted by Einstein's general theory of relativity, confirmed by decades of observation, called gravitational lensing. The gravity of a massive object bends the path of light passing near it, acting like a cosmic lens. Our sun does this, and the focal point of the sun's gravitational lens, the point where light from a distant source passing near the sun's limb would be focused and amplified, sits at a minimum distance of roughly 550 astronomical units from the sun. That is about 8.2 light hours away, well within our solar system, technically, but vastly beyond anything humans have reached so far. Voyager 1, our most distant spacecraft, has traveled about 163 astronomical units over nearly 50 years, but here is where your 1 light-year vantage point becomes extraordinary. From the right position along the sun's focal line, and that line extends outward from 550 astronomical units essentially forever, you could use the sun itself as a gravitational telescope of almost incomprehensible power. A telescope that could, in principle, resolve features on the surface of an Earth-sized planet orbiting a star dozens of light-years away, structures just meters across, features that no human-built telescope, no matter how large, could ever resolve from Earth orbit. This concept, called the Solar Gravitational Lens Mission, is not science fiction. It is a concept being seriously studied and developed by researchers including Slava Turishev at NASA's Jet Propulsion Laboratory. The science is solid, the physics is confirmed, the engineering is extraordinarily challenging but not fundamentally impossible. What it would require is a spacecraft traveling to the focal region and then maneuvering with extreme precision along the focal line while using the sun as its primary optical element. The images it could return would be unlike anything ever captured in the history of human astronomy, and the irony is beautiful. The sun, the very object whose light becomes just a faint dot when viewed from 1 light-year away, becomes, when used correctly, the most powerful telescope in the history of science. Distance transforms it from a source of warmth and life into an instrument of almost supernatural clarity. Let me bring in one more layer of reality here, because I think it fundamentally changes how you should feel about this entire conversation. When we talk about traveling 1 light-year, we are not talking about a destination in the way we usually think about travel. There is no planet waiting for you there, no surface to land on, no atmosphere to breathe. The nearest confirmed exoplanets, the planets orbiting other stars, are the ones in the Alpha Centauri system, including Proxima Centauri b, which sits about 4.24 light-years from Earth. 1 light-year gets you roughly a quarter of the way there. You are, in the most literal sense, in the middle of nowhere, in the interstellar void, with nothing around you in any direction for distances that take years of light travel to cross. But here is what makes that nothingness profound rather than bleak. You are not surrounded by absence. You are surrounded by potential, the interstellar medium around you, that tenuous magnetic particle-laced sea of ancient atomic matter, is the raw material of future stars, future planets, future chemistry, future life. Somewhere in that darkness, in clouds you cannot see with the naked eye, gravitational instabilities are quietly gathering molecular hydrogen into knots that will eventually collapse under their own weight, heat to tens of millions of degrees, ignite nuclear fusion, and become new suns. You are traveling through a stellar nursery in slow motion. You are moving through the universe's workshop, where the raw ingredients of everything that will ever exist are drifting in patient readiness. Carl Sagan once said that we are a way for the cosmos to know itself. Standing, floating, 1 light-year from Earth, you would be the furthest extension of that self-knowledge that humanity had ever reached. Every instrument you carried, every observation you made, every question you asked would be the universe turning its attention on itself through the improbable medium of a biological creature that evolved on a rocky world orbiting an unremarkable star in a galaxy of 400 billion stars. That is not nothing, that is everything. If you are enjoying this video, make sure to subscribe and give this video a thumbs up. Everyday content like this comes out. And subscribing means you never miss the moment science breaks your brain open in the best possible way. Let's talk about what you would actually see. Because this is one of those corners of physics where the mathematics and the visual reality diverge so dramatically from everyday experience that even people who understand the equations intellectually are left genuinely stunned when they see it rendered visually. What the universe looks like from inside a vessel moving at a significant fraction of the speed light travels is not what you see in movies. It is not a clean tunnel of streaking stars rushing past you like you are jumping to hyperspace. It is something far stranger, far more beautiful, and in ways that are hard to articulate until you have sat with the physics long enough for it to become visceral, deeply, uncomfortably real. The first thing that happens as your speed climbs is something called relativistic aberration. This is a phenomenon where the apparent direction of incoming light shifts based on your velocity relative to its source. In everyday life, you experience a mild version of this when you walk through rain. Even if the rain is falling perfectly straight down, it appears to angle toward your face because you are moving into it. Now scale that effect up to velocities approaching the speed light travels, and the consequences are extraordinary. As your speed increases toward a large fraction of light speed, the light coming from stars in front of you and stars to your sides, and even stars slightly behind you, gets bent forward. It all crowds toward the direction you are heading. The stars ahead of you appear to compress into a smaller and smaller region of the sky, bunching together into a brilliant, concentrated disk of light directly in front of your vessel. Meanwhile, the sky behind you grows darker and emptier as stars that were once visible at your sides get swept forward into that growing concentration ahead. At very high velocities, say 99% of the speed light travels, essentially the entire visible universe would appear compressed into a relatively small, intensely bright circle directly ahead of you. The rest of the sky would be nearly dark. You would be flying into a tunnel of light, not because the stars are physically moving, but because your motion is bending the geometry of the light reaching your eyes. And that is only the beginning of how strange the view becomes. Lost on top of aberration is the relativistic Doppler effect. You are probably familiar with the everyday version. The way an ambulance siren sounds higher pitched as it approaches you and lower pitched as it moves away. That is the Doppler effect acting on sound waves. Light behaves the same way, but with consequences that go far beyond a simple change in pitch. When you move toward a light source at relativistic speeds, the light waves compress, shifting toward the blue end of the electromagnetic spectrum. When you move away, they stretch toward the red end. This is called blue shift and red shift respectively, and at the velocities we are discussing, the shifts become extreme enough to completely transform the visual character of the light reaching you. Stars directly ahead of you, already compressed into that bright forward disk by aberration, would appear intensely blue shifted. Their visible light would shift toward ultraviolet and then into X-ray frequencies. Stars that were emitting mostly infrared radiation, invisible to your naked eye under normal circumstances, would blue shift into the visible range and suddenly appear as new stars where previously there seemed to be nothing. The forward sky would blaze with a kind of light that human eyes were never designed to process safely. You would need filters. You would need instruments to translate those frequencies back into something your biology could handle. Behind you, the opposite transformation would be underway. The stars in your rear view, the ones being swept backward by aberration, fading from the periphery of your vision, would be massively redshifted. Visible stars would shift into infrared. Infrared sources would drop into microwave frequencies. The sky behind you would not just look dark and empty, it would actually be full of radiation your eyes simply cannot detect. The stars would not have disappeared. They would have been translated into a frequency of light your biology was never built to perceive. And there is one more layer to this visual transformation that I find almost unbearably beautiful. The cosmic microwave background radiation, the faint thermal glow left over from the early universe, the afterglow of the Big Bang itself, filling all of space in every direction, at a temperature of just 2.7 degrees above absolute zero, would also experience this Doppler shift. At high enough velocities, that background radiation, which is normally a uniform, featureless microwave hiss, would blue shift into the infrared and then into visible light in the direction of your travel. The Big Bang's echo would glow. You would see the universe's birth cry lit up in front of you as visible light. There is no poetic way to improve on what the physics itself already says about that. Now let's talk about something that researchers actually spent considerable time studying using computer simulations, because the visual effects of relativistic travel are complex enough that intuition alone is completely unreliable. Groups at institutions including the University of Tübingen in Germany developed detailed simulations called real-time relativity programs, interactive environments where users could navigate a virtual space at relativistic velocities and directly observe the visual distortions produced by aberration and Doppler shifting. What they found was that the combined effect of these phenomena produces a visual experience so alien that even physicists who fully understood the underlying mathematics were surprised by what they saw when they actually rendered it. One of the most counterintuitive results from those simulations involves the apparent shape of objects. You might assume that as you fly past a sphere, say a large asteroid, at relativistic speed, it would appear flattened or distorted due to the compression of space in your direction of travel. This is what the mathematics of Lorentz contraction might naively suggest, but the visual reality, first worked out mathematically by James Turrell and Roger Penrose independently in 1959, is different. Because of the way light from different parts of the object takes slightly different amounts of time to reach your eyes, a sphere actually appears to remain spherical, but rotated. It looks like the object has twisted relative to you, not squashed, twisted. The geometry of what you see at relativistic speeds is a layered product of multiple simultaneous effects, and the result is a universe that looks like nothing in ordinary human experience. It looks, if anything, like certain styles of surrealist art, distorted in ways that feel almost intentional, almost designed, as though the cosmos were revealing the hidden architecture beneath its everyday appearance. There is another visual phenomenon worth dwelling on because it connects directly to the experience of actually navigating a relativistic spacecraft. As you accelerate, the point toward which all the stars appear to converge, that compressed disk of light ahead of you would act as a kind of false horizon. The brightest concentration of light would always be directly in your direction of travel. In a sense, the universe itself would be pointing the way. You would always know exactly which direction you were heading, not from instruments, but from the shape of the sky itself. The cosmos would be showing you the way with light, but there is a practical problem with this beautiful navigation trick. At velocities high enough to produce dramatic aberration, anything above roughly 50 or 60% of light speed, the star field in front of you would be so compressed and so intensely energized that your instruments would be facing a very different kind of incoming radiation than they were designed for. Navigation systems calibrated for the normal sky would be operating in an environment where the star catalog is effectively scrambled, stars in unexpected positions, radiating at unexpected frequencies. You would need entirely new navigation algorithms, new sensors, new ways of reading a sky that looks nothing like the one your instruments were built to interpret. This is one of the reasons that serious proposals for interstellar missions, even theoretical ones, include significant thought about guidance and navigation under relativistic conditions. It is not enough to know where you are going before you leave. You need to be able to figure out where you are while you are moving, using a sky that is actively distorting around you as your speed changes. Let's take a moment to go somewhere even deeper, because everything we have talked about so far, the aberration, the Doppler shifting, the surrealist distortion of shapes, all of that describes what the universe looks like to your eyes. But there is a level beneath the visual, a level that touches not just what you see, but what you are, and it has to do with the nature of mass itself under relativistic conditions. Here is something that Einstein's equations tell us, and that every particle accelerator ever built has confirmed beyond any reasonable doubt. As an object accelerates toward the speed light travels, its relativistic mass, the effective resistance it presents to further acceleration, increases, not a little, dramatically, exponentially. The closer you get to light speed, the more energy it takes to push you just a tiny bit faster. The universe is not just taxing your speed, it is imposing an infinitely escalating toll. At exactly the speed light travels, the energy required to accelerate a massive object becomes infinite. This is not an engineering problem. This is not a technology problem. It is a law, and it means that nothing with mass, no particle, no atom, no spacecraft, no person can ever actually reach the speed of light. Only approach it, forever approach it, never arrive. What this means for your journey is that the closer you get to that ultimate speed, the more the universe resists you. Every joule of energy you pour into your engines produces a smaller and smaller increase in velocity. You approach light speed the way you approach a mathematical asymptote, getting closer and closer while the gap never fully closes. It is one of the most elegant and profound limits in all of nature, and it is completely non-negotiable. But here is the flip side, the part that makes this limitation somehow beautiful rather than merely frustrating. Because while you can never reach light speed, you can get arbitrarily close, and the closer you get, the more dramatically time dilation works in your favor. At a high enough fraction of light speed, a human lifetime becomes enough time to cross not just one light year, but dozens, hundreds. The galaxy itself, 100,000 light years across, becomes in principle traversable within a single human lifetime if you could reach a high enough fraction of light speed. Not for the people back on Earth. For them, 100,000 years would pass. But for the traveler, the relativistic compression of experienced time could make it manageable. The universe gives with one hand and takes with the other. It says you cannot reach light speed. But it also says the closer you get, the more I compress your experience of time. You cannot cheat the distance, but you can, in a sense, cheat the clock. It is one of the most extraordinary bargains in all of physics, and it is built directly into the structure of space-time itself. Now, I want to bring something into this conversation that most people have never considered in the context of relativistic travel, and it connects to one of the most fundamental questions in all of science. What is time, really? Not the practical definition, not hours and minutes and seconds measured by atomic transitions, but what is it at its core as a feature of the physical universe? Physicists today are genuinely divided on this question in ways that might surprise you. One of the dominant frameworks in modern physics, the block universe interpretation of general relativity, suggests that time is not something that flows, it does not pass. It simply exists the way space exists. Past, present, and future are all equally real, all equally present in the four-dimensional structure of space-time. What we experience as the flow of time, the sense of a moving present moment, of things happening in sequence, is, in this view, a product of our particular perspective as observers embedded in that structure. We are moving through time the way we move through space. But the whole of it is already there. If that is true, and it is taken seriously by a significant number of physicists, then on your journey to one light year, you are not just moving through space. You are tracing a path through a four-dimensional structure in which every moment of your journey, every moment of your life on Earth before departure, every moment of everything that will ever happen to you, is already in some sense there. Fixed, complete, your world line through space-time is a sculpture, and you are simply becoming aware of each part of it in sequence. That idea will either fill you with a deep sense of peace or a deep sense of unease, possibly both simultaneously, which, if you ask me, is exactly where the best science tends to live, right at the edge of what your intuition can hold. There is a question that space agencies around the world have been quietly wrestling with for decades. It does not make headlines the way rocket engines and telescope discoveries do. It does not generate the same breathless excitement as the detection of a new exoplanet or the first image of a black hole. But in many ways, it is the most important question standing between humanity and the stars. And it is this: what does profound extended isolation actually do to the human mind? Not the surface-level answer, not people get sad or people get lonely. The deep answer, the neurological answer, the answer that emerges when you look at what happens to human cognition, perception, identity, and consciousness when you strip away every environmental cue that evolution spent 4 billion years calibrating your brain to expect. Because here is the thing: your brain is not a passive receiver of reality. It is an active prediction machine. Every moment of every day, your nervous system is running sophisticated models of the world around you, anticipating sensory input, filling in gaps, constructing a coherent experience of reality from incomplete information. This is why optical illusions work. This is why you can recognize a friend's face even in poor lighting. This is why you can read a sentence even when several letters are missing. Your brain does not wait for complete information. It predicts, it fills in, it constructs. And the raw material for those predictions, the training data that your brain has been refining since the moment you were born, is Earth, gravity pulling consistently downward, a cycle of light and darkness repeating every 24 hours, the smell of air, of soil, of other living things, the sound of wind, of rain, of the biological world humming around you, the feeling of a surface beneath your feet, resisting your weight, giving your vestibular system the constant feedback it needs to know which way is down. Remove all of that, and your brain does not simply adapt gracefully, it begins in subtle and then increasingly significant ways to lose its footing. Researchers studying long-duration spaceflight have documented something fascinating and genuinely unsettling. Astronauts aboard the International Space Station, even on missions lasting only 6 months, frequently report changes in perception that go beyond what they expected. Visual processing shifts. The brain, deprived of normal gravitational cues, begins reweighting its sensory inputs, relying more heavily on vision to determine orientation, while the vestibular system, confused by the absence of a consistent gravitational reference, sends conflicting signals. This can produce a persistent, low-grade disorientation that astronauts describe as feeling slightly off, not dramatically impaired, but subtly, constantly not quite right. More striking are the structural changes that neuroimaging has revealed. Studies published in scientific journals, including the New England Journal of Medicine, based on MRI scans of astronauts before and after long-duration missions, showed measurable shifts in brain structure. Cerebrospinal fluid, the clear liquid that cushions and protects the brain, redistributes in microgravity, shifting upward toward the skull. This causes a narrowing of the spaces at the top of the brain and a compression of certain structures that does not fully reverse even after months back on Earth. Some astronauts showed changes in white matter, the connective tissue of the brain, and alterations in the volume of specific regions involved in spatial processing and motor control. Now, those are 6-month missions in the relative comfort of the International Space Station, with regular video calls home, with resupply ships arriving every few months, with the knowledge that Earth is just 400 kilometers below you, that a rescue is theoretically possible, that you are surrounded by colleagues, that you will be going home on a journey to 1 light year. None of those safety nets exist. The mission duration, even under the most optimistic assumptions about propulsion technology, would be measured in years of subjective experience. The distance from Earth would render rescue not just difficult, but categorically impossible. And the silence, the communication delay stretching from minutes to months to eventually a full year each way, would progressively sever every real-time connection to the world that shaped you. What the research on extreme isolation suggests is that the human mind under those conditions does not simply deteriorate, it transforms, and the nature of that transformation is something that researchers, philosophers, and the rare individuals who have experienced prolonged solitude all describe in remarkably consistent terms, even across vastly different cultural and historical contexts. The first phase, documented consistently in analog isolation studies from Antarctic winters to extended solo sailing voyages, is a period of heightened anxiety and hypervigilance. The brain, sensing an environment it cannot fully model, ramps up its threat detection systems. Small sounds become significant, ambiguous sensations demand interpretation, sleep becomes fragmented and irregular. Decision-making narrows, becoming more cautious and more rule-bound. This is the nervous system doing exactly what it evolved to do, treating an unfamiliar environment as potentially dangerous until proven otherwise. The second phase, if the individual has the psychological resources to move through the first, is more interesting. It is characterized by a kind of cognitive restructuring. The brain, having exhausted its anxious scanning of an environment that never produces the threats it was anticipating, begins to reorganize. Attention turns inward. The narrative self, the part of your mind that constantly constructs and maintains the story of who you are, where you came from, what matters to you, becomes more prominent, more reflective, more examined. People in extended isolation almost universally report a period of intense autobiographical recollection, as though the mind, with fewer external demands on its attention, turns its full processing power toward the question of identity. And then, for those who move through both earlier phases, something shifts again. Researchers and experiencers alike describe a third stage that is harder to categorize in purely clinical terms, a kind of expansion, a loosening of the tight defensive boundary between self and environment, a growing sense of connection, not to other people, since they are physically absent, but to something larger, to the context, to the cosmos. Polar explorers describe it, long-duration solo sailors describe it, monks in extended retreats describe it, and the handful of astronauts who have spoken most openly about their inner experience in space describe something adjacent to it, a dissolving of the ordinary sense of separateness, replaced by something that feels like participation in something vast. Now, I want to be scientifically careful here, because this territory sits at the boundary between empirical research and subjective experience, and both deserve respect without either being inflated beyond what the evidence actually supports. We do not have a rigorous, peer-reviewed account of what a years-long interstellar journey would do to human consciousness. No one has made that journey. What we have are data points from shorter, less extreme experiences, and the theoretical extrapolations of psychologists, neuroscientists, and philosophers working from those data points. But what those extrapolations suggest is genuinely compelling, because they point toward a possibility that is, I think, one of the most profound implications of interstellar travel that almost no one talks about. The possibility that the journey itself, the experience of moving through interstellar space, of being that far from Earth, of being wrapped in that specific quality of darkness and silence and distance, might produce a form of human experience that has no precedent, that has never existed before in the 4 billion-year history of life on this planet, a mode of consciousness shaped not by evolution's requirements but by the cosmos itself. You would be the first human being to think thoughts in that context, to feel what it feels like to exist at that remove from everything your species has ever known, to look at the sun as just another star and feel whatever that feeling actually is. Not as an intellectual exercise, not as something described to you by someone who looked at a rendering on a screen, but as a direct, lived, irreversible experience. Those thoughts, those feelings, those perceptions, they would be genuinely new in the universe. They would be the universe experiencing itself in a way it has never experienced itself before. Let's layer in something that the neuroscience of isolation research has uncovered that I find particularly striking. One of the most consistent findings across isolation studies is the transformation of time perception. In normal life, your sense of time passing is anchored by external rhythms, the light-dark cycle of day and night, meal times, social interactions, scheduled activities, the rhythms of other people's lives flowing around yours. These external anchors synchronize your internal biological clock, your circadian rhythm, with a 24-hour rotation of the Earth. Strip them away, and the internal clock begins to drift. Studies done in underground isolation chambers, where volunteers spent weeks or months without any external time cues, revealed that the free-running human circadian rhythm is not exactly 24 hours. It averages closer to 24 hours and 11 minutes in most people, sometimes longer. Without external correction, the internal clock drifts. Days lengthen slightly, sleep cycles shift. Over weeks and months, a person isolated from all external time cues can find themselves living on a completely different schedule than the world outside, sleeping when others are awake, awake when others are sleeping. Their internal sense of time having drifted silently away from the external standard. On a vessel in interstellar space, there is no sun rising and setting, no natural light cycle to anchor your biology, no seasonal change, no weather, no ecological rhythm of any kind. Your circadian system would be operating entirely on artificial cues, scheduled lighting, scheduled meal times, structured activities, maintained entirely by technology and intention. And the research suggests that even with those artificial anchors, the biological and psychological experience of time itself changes in extended isolation. Time becomes less linear, less granular, more like a flowing continuum. Individual days blur, weeks lose their distinctiveness. The mind, freed from the relentless chopping of experience into discrete units, begins to experience duration differently, whether that is disorienting or liberating, or both, in alternating waves. Likely depends on the individual. But it points towards something important about what the journey would actually feel like from the inside, not a series of days ticked off a calendar. Something more fluid, more continuous, more like the cosmos itself, which does not run on human schedules, does not organize itself into mornings and evenings, does not care what day of the week it is. There is one more dimension of the psychological experience I want to explore before we move on, because I think it might be the most personally affecting of all, and it has to do with meaning, with purpose, with the most fundamental human question: why? Every long-duration mission study, every account from explorers and isolated individuals eventually circles back to this. The people who fare best psychologically in extreme isolation are not necessarily the ones with the strongest bodies or the highest cognitive scores. They are the ones with the most robust sense of meaning. The ones who know, at a deep and unshakable level, why they are doing what they are doing. Whose mission is not just an assignment but a calling. Who can look at the darkness around them and feel, not terror, but purpose. Viktor Frankl, the Austrian psychiatrist who survived the Nazi concentration camps and went on to develop an entire school of psychotherapy around the primacy of meaning, wrote that human beings can endure almost anyhow if they have a sufficient why. That insight, forged in one of the most extreme crucibles of human suffering ever recorded, resonates with profound relevance for the question of interstellar travel. The journey to 1 light year would demand a why of extraordinary depth and durability, a reason strong enough to survive years of isolation, physical hardship, temporal dislocation, and the crushing weight of distance. Something that could hold its meaning even when you look out the window and see only darkness in every direction, and the sun has faded to just another point of light, and everyone you have ever known is 1 year's worth of signal delay away. What would that why look like? For some, it might be the science, the irreplaceable data, the observations, the measurements that only this vantage point could provide. For others, it might be something more philosophical, the act of being there, of extending human presence and awareness into a space it has never occupied, of being the living edge of human curiosity. And for others still, it might be the most ancient motivation of all, the need to go, to see, to know. The same impulse that sent the first humans walking across ice bridges between continents, that drove Polynesian navigators across the Pacific using nothing but stars and ocean currents. That pushed every explorer who ever stood at the edge of the known world and took one more step forward into the unknown. We are made for this, not physically. Physically, we are fragile and ill-adapted for space, as we have been discussing. But psychologically, motivationally, spiritually, we are a species of boundary crossers, a species that looks at horizons and feels not satisfaction but hunger. The cosmos did not produce us by accident. 4 billion years of evolution on a water-wrapped, magnetically shielded, atmospherically cushioned world produced a creature that looks up at the stars and wonders. That is not a small thing. That is the universe developing eyes with which to see itself and a heart with which to long for what it sees. 1 light year, 9.46 trillion kilometers of darkness, radiation, magnetic fields, and ancient atomic matter. And somewhere in that darkness, a single vessel carrying the most improbable cargo in the known universe, a conscious mind asking questions, reaching outward, refusing to stay home. Let's talk about scale, real scale. Not the kind that fits comfortably in your imagination, but the kind that actively resists it. The kind that pushes back against every attempt your mind makes to contain it, and in doing so, reveals something extraordinary about the nature of the universe and our place within it. Because one of the most important things a journey of 1 light year can do for you, perhaps the most important thing, is show you with brutal and beautiful clarity exactly how small that distance actually is. Here is a way to feel it rather than just hear it. Imagine the entire Milky Way galaxy, our galaxy, the one containing our sun, our solar system, every star you have ever seen with your naked eye on a clear night, shrunk down to the size of a standard dinner plate, roughly 30 centimeters across. On that scale, where does 1 light year sit? 1 light year on a dinner plate Milky Way is approximately the width of a single human hair. Not the plate, not a slice of it, a hair, one strand. Pressed against the surface of a plate that represents a structure containing somewhere between 200 billion and 400 billion stars, stretching 100,000 light years from edge to edge and 2,000 light years thick at the disk. That is not a comfortable thought. It should not be. But it is an honest one, and honesty about scale is one of the greatest gifts that astronomy has ever given to our species. Now let's build outward from that hair's width and see what the universe actually contains at increasing distances. Because the architecture of what lies beyond 1 light year is one of the most jaw-dropping things science has ever mapped. At roughly 4.24 light years from Earth sits the Alpha Centauri system, the closest stellar system to our Sun. It is actually a triple star system, 2 sun-like stars, Alpha Centauri A and Alpha Centauri B, orbiting each other in a gravitational dance, and a third, much smaller companion, Proxima Centauri, a red dwarf that happens to be the closest of the 3 to us and holds, in orbit around it, at least one confirmed rocky planet. That planet, Proxima Centauri b, sits within what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a planetary surface. Whether it actually does is a question we cannot yet answer. Proxima Centauri is a volatile, flare-prone star, regularly blasting its nearby planets with intense ultraviolet and X-ray radiation in events far more powerful than anything our own sun produces. Whether life, or even an atmosphere, could survive that battering is one of the most actively debated questions in astrobiology right now. But here is the staggering point. 4.24 light years, the closest star system to ours, likely containing at least one rocky planet, possibly multiple worlds, and we just spent this entire video establishing how impossibly, almost inconceivably far 1 light year is. Proxima Centauri is 4 times further than that, the nearest neighbor, our cosmic next-door neighbor, and it sits at a distance that would take our current fastest spacecraft, traveling at roughly 17 kilometers per second, approximately 73,000 years to reach. Let that land. 73,000 years, human civilization as we currently define it. Cities, writing, agriculture, recorded history is roughly 10,000 years old. We would need to repeat the entire span of human civilization 7 times over just to cross the gap to the nearest star at our current best speed. But let's keep going outward, because the architecture of what lies beyond gets progressively more extraordinary at every scale. At about 25,000 light-years from Earth, you reach the center of our galaxy, the galactic center. a region of the Milky Way so dense with stars that the night sky there, if any planet orbiting any of those stars happened to have eyes looking up, would blaze with a brightness tens of thousands of times greater than what we see from our quiet outpost in the Orion Arm. And at the very heart of that central region sits something that took astronomers decades to confirm and that earned the scientists who proved it a Nobel Prize in Physics in 2020. A supermassive black hole. We call it Sagittarius A star. It contains a mass of roughly 4 million times that of our Sun, compressed into a region smaller than the distance between our Sun and the nearest planets in our solar system. It is not actively feeding at the moment. It is what astronomers call quiescent, but its gravitational influence dominates the entire central region of the galaxy, and stars orbit it at extraordinary speeds. The star designated S2 completes a full orbit around Sagittarius A star in just under 16 years, reaching speeds of nearly 3% of the speed light travels at its closest approach. Watching S2's orbit was one of the key pieces of evidence that confirmed the black hole's existence and mass: 25,000 light-years, 25,000 of those dinner plate hairs. And we are still inside our own galaxy. At 100,000 light-years, you reach the far edge of the Milky Way's disk. Step beyond that, and you enter what astronomers call the local group, the gravitationally bound collection of galaxies that the Milky Way calls home. The local group contains more than 50 galaxies, though most of them are small dwarf galaxies, irregular collections of a few billion stars or less, orbiting the two dominant members of the group like satellites. Those two dominants are us, the Milky Way, and our nearest large galactic neighbor, the Andromeda Galaxy, designated Messier 31, sitting approximately 2.5 million light-years away. Andromeda is the most distant object visible to the naked human eye under dark skies. It appears as a faint, smudged patch of light, and what you are seeing when you look at it is the combined light of roughly 1 trillion stars, arriving at your retina after traveling 2.5 million years. The light reaching your eyes right now left Andromeda when our ancestors were early members of the genus Homo, walking the African savanna, not yet having developed language, not yet having made their first stone tools of the kind that define the archaeological record of that era. That light has been traveling since before our species as we know it existed, and it is arriving now, tonight, at your eyes, if you know where to look and the sky is dark enough. Andromeda is also on a collision course with the Milky Way. In roughly 4.5 billion years, give or take, the two galaxies will begin a slow, graceful gravitational merger that will unfold over hundreds of millions of years. The result will be a new, larger elliptical galaxy, sometimes informally called Milkomeda by astronomers who enjoy naming things with a certain flair. Individual stars are so far apart that the physical collision of stars during this merger is extraordinarily unlikely, but the gas clouds will collide, compress, and trigger enormous waves of star formation, new suns blazing into existence as two galaxies become one. It will be one of the most spectacular events in the future history of our corner of the cosmos, and it is already underway. In the slow-motion language of gravitational dynamics, step back further still, out to roughly 54 million light-years, and you reach the Virgo cluster, the nearest large galaxy cluster to our local group, containing roughly 1,300 galaxies bound together by their mutual gravity. The Virgo cluster is itself the gravitational heart of a much larger structure called the Virgo supercluster, of which our local group is a small outlying member. And then, in 2014, a team of astronomers led by Brent Tully at the University of Hawaii published a landmark paper in the journal Nature that redefined what we mean by our cosmic home, using a technique that maps the flow of galaxies toward gravitational attractors. essentially tracing the cosmic web of gravity by watching how galaxies move. They defined an enormous superstructure of which the Virgo supercluster is just one part. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains the mass of roughly 100 million billion suns, spans approximately 500 million light-years, and contains an estimated 100,000 galaxies. Our Milky Way sits near the outer edge of this structure, a small galaxy in a small group, on the periphery of one lobe of a vast cosmic web of matter that was shaped by the interplay of gravity and dark energy over the 13.8 billion years since the Big Bang, 500 million light-years. And we are still talking about one structure, one supercluster, in a universe that contains an estimated 2 trillion galaxies in total, distributed across a region at least 93 billion light-years in diameter and possibly infinite in extent. Now bring all of that back to one light-year, one hair on one dinner plate, and ask yourself, what does that do to your sense of scale? What does it do to your sense of significance? Because here is the thing that I think gets missed in most conversations about cosmic scale. The instinctive response to numbers like these is a kind of diminishment, a feeling of smallness that can tip into meaninglessness. If the universe is that vast, if our galaxy is that enormous, if our solar system is that negligible, then what are we? What does anything we do matter? But I want to push back against that response. Not with false comfort, not with empty reassurance, but with something more interesting, with the actual implications of what the science tells us. Because the universe being this vast does not make us insignificant. It makes us extraordinary. Here is why. In all of those 2 trillion galaxies, in all of that immeasurable, ancient, sprawling complexity, we know of exactly one place where matter has arranged itself in such a way that it can look back at the universe and ask what the universe is. One confirmed location where the cosmos has produced something capable of curiosity, of wonder, of the specific, beautiful, improbable act of trying to understand the context it finds itself in. That is here, that is us. And the rarity of that, the astonishing improbability of a universe that generates beings who can comprehend it, is not a reason for despair. It is a reason for something close to reverence. Carl Sagan captured it better than almost anyone when he described the cosmos as within us, that we are made of star stuff, that we are a way for the universe to know itself. But I want to add a layer to that. Not only are we made of the same atoms as stars and galaxies, not only are we the product of the same physical laws that govern black holes and supernovae, we are, as far as we know, the universe's most complex achievement, the densest, most intricate arrangement of matter and energy that 13.8 billion years of cosmic evolution has produced anywhere we have been able to look. Your brain, the organ that is processing these words and ideas right now, contains approximately 86 billion neurons, each connected to thousands of others through synaptic connections that number in the hundreds of trillions. The total number of possible states of connection in a human brain exceeds the number of atoms in the observable universe. You are, structurally, more complex than a galaxy, not more massive, not more energetic, but more complex, and complexity, the capacity to encode, process, and generate meaning, may be the most remarkable thing the universe has ever produced. There is something else that the scale of the cosmos reveals, something that modern cosmology has only recently begun to fully appreciate. The universe is not uniformly distributed. Matter does not spread evenly through space like butter on bread. It clumps, it webs, it filaments. On the largest scales, the distribution of galaxies in the universe forms a structure so vast and so intricate that when cosmologists first mapped it comprehensively, using surveys like the Sloan Digital Sky Survey, which catalogued the positions and distances of hundreds of millions of galaxies, what they found looked like nothing so much as a three-dimensional web, sheets and filaments of galaxies separated by enormous voids, regions of space hundreds of millions of light-years across that contain almost no galaxies at all. This structure is called the cosmic web, and it is one of the most stunning visual and conceptual products of modern cosmology. The filaments of the cosmic web are not just concentrations of visible matter. They trace the underlying distribution of dark matter, the mysterious invisible substance that makes up roughly 27% of the total energy content of the universe, that interacts with ordinary matter only through gravity, that has never been directly detected despite decades of searching, but whose gravitational fingerprints are visible in the motion of galaxies, the bending of light, and the large-scale structure of the cosmos itself. Without dark matter, galaxies as we know them would not exist. The gravitational seeds needed to draw ordinary matter together into the first stars and galaxies required more mass than ordinary matter alone could provide. Dark matter provided that scaffolding. The cosmic web, the largest structure in the observable universe, was built on a skeleton of something we cannot see, cannot touch, and cannot yet identify, and all of it, the web, the filaments, the voids, the clusters, the superclusters, the galaxies, the stars, the planets, the chemistry, the biology, the minds doing the observing, all of it traces back to a moment 13.8 billion years ago, when the universe was smaller than a proton, hotter than any temperature that has existed since, and in a state of almost perfect uniformity that was nevertheless not quite perfect. Those tiny, quantum-scale fluctuations in the early universe, fluctuations so small they seem inconsequential, grew under gravity into everything you see when you look up at the night sky. The cosmic web is the amplified echo of quantum uncertainty in the first moments after the Big Bang. You are looking at quantum mechanics written large across the sky. I want to leave you with one more thought, because I think it reframes the entire journey we have been describing in a way that cuts straight to the heart of why any of this matters. When you travel 1 light year from Earth, when you make that crossing into interstellar space, past the edge of the heliosphere, through the interstellar medium, out to that point where the Sun is just one more star among thousands, you carry something with you that nothing else in the observable universe is known to carry. You carry a story, not just the story of your own life, though that is part of it. You carry the 4 billion year story of life on Earth, the 3.5 billion year story of evolution by natural selection, the 300,000 year story of Homo sapiens, the 10,000 year story of civilization, the few hundred year story of science, the decades-long story of space exploration. All of that compressed into roughly 70 kilograms of organized, self-aware matter floating through interstellar space, looking back at a pale dot and thinking about it. No galaxy does that. No nebula does that. No black hole, no neutron star, no supernova does that. Thinking about it, turning the universe's own matter into an instrument of self-reflection, is, as far as we know, exclusively what life does, what minds do, what you do every time you look up at the sky and wonder. 1 light year is nothing on the cosmic scale, and it is everything on the human one. Let's talk about the ship, because everything we have explored so far, the time dilation, the radiation, the psychological transformation, the cosmic scale, all of it assumes that your vessel survives the journey. And that assumption, when you actually examine it through the lens of physics and engineering, turns out to be one of the most demanding and least discussed challenges in the entire enterprise of interstellar travel. The cosmos is not just indifferent to your presence out there. In certain very specific and very physical ways, it actively tries to take your ship apart. And the most surprising threat is not what most people imagine. It is not a rogue asteroid. It is not a solar flare. It is not even the radiation we talked about in a while ago. devastating as that is. The most dangerous thing your spacecraft will face at relativistic velocities is something so small it is invisible to the naked eye: interstellar dust. Tiny grains of silicate and carbon compounds, some of them smaller than a bacterium, drifting silently through the interstellar medium at essentially zero velocity relative to the galaxy. Under ordinary circumstances, at the speeds of conventional spacecraft, these particles are negligible. But when you are moving at a significant fraction of the speed light travels, the situation transforms completely. And the physics of what happens is both elegant and terrifying. Here is the core of the problem. Kinetic energy scales with the square of velocity. Double your speed, and the kinetic energy of a collision does not double, it quadruples. Triple your speed, and it increases by a factor of 9. Now scale your speed to 10% of the speed light travels, which is already an almost incomprehensible achievement, far beyond anything we have ever built, and the numbers become extraordinary. A single dust grain with a mass of just 1 microgram, 1/1,000,000th of a gram, smaller than a grain of pollen, hitting your spacecraft at 10% of light speed carries kinetic energy comparable to a rifle bullet. At 50% of light speed, that same invisible speck hits with the energy of a hand grenade. At 90%, we are talking about something approaching a small explosive charge, delivered to your hull by a particle you cannot see, cannot detect in advance with any currently existing technology, and cannot steer around because there is no way to map every grain of dust in the interstellar medium along your path. And the interstellar medium, sparse as it is, remember, we are talking about sometimes just 1 atom per cubic centimeter, still contains enough dust to make this a genuine, unavoidable, potentially catastrophic problem over the course of a 1 light-year journey. Astronomers estimate roughly 1 dust grain per million cubic meters in typical interstellar space. Spread that across the cross-sectional area of even a small spacecraft over 9.46 trillion kilometers of travel, and the cumulative number of impacts becomes significant, not occasional, not rare, significant. This is not a hypothetical concern invented for the purposes of this conversation. It is one of the central engineering challenges studied by researchers working on projects like Breakthrough Starshot. The initiative, funded in part by the late Stephen Hawking and Russian billionaire Yuri Milner, announced in 2016, which proposed sending a fleet of gram-scale laser-propelled spacecraft, essentially tiny sails, to the Alpha Centauri system at roughly 20% of light speed. One of the primary engineering problems the Breakthrough Starshot team identified and has been working to address is exactly this. How do you protect a spacecraft from interstellar dust impacts at relativistic velocities when the dust is essentially invisible, essentially unpredictable, and essentially unavoidable? Several solutions have been proposed, and each one reveals something interesting about the ingenuity and the limitations of human engineering in the face of cosmic physics. The first and most straightforward approach is simply to make the leading face of the spacecraft as small as possible and as hard as possible. A smaller cross-sectional area means fewer impacts per unit of distance traveled. A harder, denser material on the forward surface, beryllium, certain ceramics, or even a thin layer of carbon in a highly compressed crystalline form, can absorb and distribute the energy of small impacts without catastrophic failure. The Breakthrough Starshot sail design, for instance, is essentially a flat chip, gram scale, centimeter scale in cross-section, minimizing the target area to the point where the probability of a catastrophic impact over the journey is reduced to acceptable levels. But that works for a gram-scale spacecraft. For a vessel large enough to carry a human being, the cross-sectional area is orders of magnitude larger, and the problem scales accordingly. The second approach is active shielding, some kind of electromagnetic or plasma shield projected ahead of the spacecraft to deflect incoming particles before they reach the hull. This is the kind of idea that sounds like pure science fiction but has genuine scientific grounding. Charged particles, which include a significant fraction of the interstellar medium, can be deflected by magnetic fields. A powerful superconducting magnet generating a strong enough field ahead of the spacecraft could in principle push charged particles out of the ship's path. This is actually related to the concept of a magnetic sail, which has been studied not just as a radiation shield, but as a potential propulsion mechanism, using the pressure of the interstellar medium itself to decelerate a spacecraft arriving at its destination. The challenge is that not everything in the interstellar medium is charged. Neutral dust grains, electrically balanced particles that do not respond to magnetic fields, would pass straight through any electromagnetic shield as though it were not there. A third approach combines both ideas with something more exotic, a plasma shield. If you could project a cone of ionized plasma ahead of your spacecraft, neutral dust particles entering the plasma cone would be ionized, stripped of their electrons, and then deflected by the magnetic field component of the shield. In principle, this could address both charged and neutral threats. In practice, generating and maintaining such a shield across interstellar distances with the energy constraints of any realistic spacecraft is an engineering challenge that remains firmly in the territory of active research rather than solved problem. But dust is not the only structural threat your spacecraft faces. There is something else, something more subtle, less immediately dramatic, but equally real over the timescale of an interstellar journey. And it has to do with the behavior of materials themselves in the deep, cold and hard radiation of interstellar space. The temperature of the interstellar medium, the actual thermal temperature of the gas, varies enormously depending on what phase of the medium you are passing through. In the warm ionized medium that fills much of the volume between star systems, temperatures can reach around 8,000 degrees. But that sounds misleading because the density is so incredibly low, so few atoms per cubic centimeter, that the actual heat content is negligible. Your spacecraft would not feel warm passing through it. The effective temperature experienced by your hull would be determined primarily by the cosmic microwave background radiation, that 2.7-degree thermal bath we discussed earlier, and by whatever waste heat your own systems generate. In the absence of a nearby star, in the true interstellar void, your spacecraft's exterior would eventually equilibrate to temperatures close to absolute zero. The kind of cold that makes materials brittle, the kind of cold that causes differential thermal contraction between components made of different substances, the kind of cold that, over years and decades, stresses welds and joints and seals in ways that room temperature engineering does not fully anticipate. Radiation compounds this. The constant bombardment of cosmic rays we discussed does not just threaten biological tissue, it damages electronics. High-energy particles passing through semiconductor components can flip individual bits in computer memory, an effect called a single event upset, causing calculation errors, software corruption, and hardware failures. Spacecraft operating in the radiation-intense environment beyond Earth's protective magnetic field already deal with this. Deep space missions use radiation-hardened electronics, components built with larger transistors and more robust error correction systems designed to tolerate a higher rate of particle hits without catastrophic failure. But interstellar space, beyond the heliosphere's protection, presents a radiation environment more intense and more sustained than anything our existing spacecraft have been designed to handle for the durations of an interstellar journey. Over years of exposure, the cumulative damage to unshielded electronics would be severe, Memory errors would accumulate, processing would degrade, and in a vessel carrying humans, where the electronics govern everything from life support to navigation to medical systems, the reliability requirements are not just high, they are absolute. A failed navigation system 1 light-year from Earth is not a problem you can call a repair crew to fix. It is a problem you solve with whatever is on board, or you do not solve it at all. This brings us to something that I think is one of the most underappreciated aspects of interstellar mission design, and one that reveals a profound truth about the relationship between technology and the cosmos. The challenge of an interstellar journey is not primarily a propulsion challenge, it is a reliability challenge. Getting to high velocity is extraordinarily difficult, yes, but keeping a complex system functional autonomously without external support across years or decades of operation in the most hostile environment our species has ever considered entering is in many ways the harder problem. Every system on your spacecraft must function perfectly, or near perfectly, for the entire duration of the mission. There are no mechanics to call, no replacement parts to order, no software patches to download from mission control with a 1-year communication delay. Every component that might fail must have a redundant backup. Every backup must itself be redundant. Every critical system must be designed to detect its own failures and either repair itself or switch to an alternative without human intervention. And all of that redundancy, all of that self-diagnostic capability adds mass, and mass in a relativistic spacecraft is the enemy, because the more mass you carry, the more energy it takes to accelerate it to the speeds the journey demands. There is a beautiful, brutal tension at the heart of interstellar engineering. You need more systems to be safe. More systems means more mass. More mass means more energy to accelerate. More energy means larger fuel stores. Larger fuel stores means more mass, which means more energy, which means more fuel. The engineering spiral goes around and around, and every loop tightens the constraints further. The universe does not make this easy. It was not designed to. It does not care about our ambitions. It simply presents its laws: conservation of energy, the relationship between mass and velocity, the inverse square of radiation intensity, the kinetics of dust impacts, and invites us to be clever enough to work within them. Let me tell you about one of the most creative and genuinely fascinating propulsion concepts that researchers have seriously studied for interstellar travel, because it approaches the mass problem from a completely different angle. Rather than carrying fuel at all, rather than launching from Earth with everything you need for the journey already on board, this concept, called a Bussard Ramjet, was proposed by physicist Robert Bussard in 1960, and it is one of those ideas that is so elegant it almost seems like it was designed by the universe rather than discovered by a human being. The concept works like this. Interstellar space, as we have established, contains hydrogen, sparse but present, at roughly 1 atom per cubic centimeter in typical regions. A Bussard ramjet would scoop that hydrogen from the interstellar medium using an enormous electromagnetic funnel, potentially hundreds of kilometers in diameter, and feed it into a fusion reactor, using the energy released by nuclear fusion to both power the ship and provide thrust. In principle, the faster the ship goes, the more hydrogen it scoops per second, creating a kind of positive feedback loop of acceleration. The ship would not need to carry fuel at all. It would harvest fuel from the very medium it is traveling through. The elegance of this idea is genuinely breathtaking. It transforms the interstellar medium from an obstacle, a sea of radiation, dust and particle threats, into a resource, into fuel. It is one of those conceptual reversals that the best science and engineering sometimes produces, where what initially appeared to be the problem turns out to be the solution. The practical difficulties, unfortunately, are severe. The density of hydrogen in the interstellar medium turns out to be much lower than Bussard originally assumed when he calculated how large the scoop would need to be. More recent calculations suggest that the scoop would need to be extraordinarily large, potentially thousands of kilometers across, to gather hydrogen at a sufficient rate for the fusion reactor to run, and the electromagnetic field required to funnel neutral hydrogen, which again does not respond easily to magnetic fields, would itself require an enormous energy investment. Subsequent analysis by physicists including Tony Martin and Robert Zubrin suggested that the drag produced by the scoop's interaction with the interstellar medium might actually exceed the thrust produced by the fusion reactor, meaning the ramjet might decelerate rather than accelerate. But here is what matters about the Bussard ramjet beyond its current technical limitations. It represents a mode of thinking that is essential to the long-term project of interstellar travel. It asks, what is already out there? What does the cosmos provide? Rather than assuming we must bring everything from home, it looks at the environment of deep space and asks what resources exist within it that could be harnessed. That question, what does the universe give us to work with, is going to be at the center of every serious interstellar engineering discussion for decades to come. And the answers, when they arrive, will likely be as surprising and as counterintuitive as the best ideas in the history of science. There is one more engineering reality I want to address, one that is less about propulsion or shielding and more about the fundamental nature of the mission itself. And it is this: how do you decelerate? This is the question that often gets skipped in popular discussions of interstellar travel, and it is arguably more difficult than the acceleration problem. Getting up to speed is hard, but arriving at your destination at near light speed and having any hope of actually doing something useful when you get there requires slowing down, and slowing down requires either carrying deceleration fuel, which adds massively to the initial launch mass, or finding some other mechanism to shed velocity at the destination. Some proposals use a laser sail concept not just for acceleration, but for deceleration, a second laser array built at the destination system that would push against the incoming sail to slow it. For an unmanned probe, this is conceivable. For a crewed vessel arriving at a star system where no infrastructure exists, it requires either extraordinary foresight, sending construction equipment years ahead of the crew, or a fundamentally different approach to the deceleration problem. One creative solution involves using the destination star's own light pressure for deceleration, a kind of stellar braking where the photon pressure from the target star gradually slows an incoming light sail. The physics works, the time scales are long, and the deceleration is gentle, but over the final approaches of an interstellar journey, gentle and long might be exactly what is available, and available is worth a great deal when the alternative is arriving at 20% of light speed with no way to stop. The universe, in its characteristic way, provides the tools, but it does not make using them simple. 120 years ago, powered flight did not exist. 60 years ago, no human being had left Earth's atmosphere. 50 years ago, we walked on the moon. Today, private companies are routinely launching rockets and landing them vertically on drone ships in the middle of the ocean, something that would have seemed like pure fantasy to the engineers of the Apollo era. The pace of technological development is not linear, it accelerates, and the gap between where we are now and where we need to be for interstellar travel, while genuinely vast, is a gap made of engineering problems that physics has already told us are not fundamentally impossible. The stars are not forbidden to us by nature. They are simply very far away, and we are very early in our story. If you are still watching, it means this channel was made for you. Don't forget to give this video a like and hit the subscribe button. It takes 1 second, but makes all the difference. Your support means the world to me. There is an idea that has lived at the intersection of science and human imagination for nearly a century. It surfaces in the works of early visionary thinkers like Konstantin Tsiolkovsky, the Russian rocket pioneer, who first sketched the concept in the early 1900s. It appears in the writings of J.D. Bernal, the Irish physicist who in 1929 described enormous hollow spheres carrying self-sustaining human communities through interstellar space. It has been explored by biologists, sociologists, geneticists, architects, and anthropologists because it is not purely an engineering problem. It is a human problem, a civilization problem, and in many ways, it is the most honest answer to the question of how our species might actually, practically, realistically cross the gulf between the stars. It is the generation ship. A vessel so large, so self-contained, so completely closed as an ecological and social system that it does not need to arrive within a single human lifetime. It carries not just travelers, but an entire living community. People who are born aboard, who live their whole lives aboard, who raise children aboard, who grow old and die aboard, while the ship moves steadily through the interstellar dark toward a destination that no one currently alive on it will live to see. The people who arrive at the destination star will be the great-great-great-grandchildren of the people who departed Earth. The journey itself becomes the world, the ship becomes home. Not a temporary conveyance, a civilization in motion. Let's think about the scale of what this actually requires, because a generation ship is not a spacecraft in any conventional sense. It is something closer to a small city, or more precisely, a small closed biosphere. Everything that sustains human life must be contained within it and continuously recycled with near-perfect efficiency. Water, air, food, soil microbiomes, the full biological complexity of a living ecosystem compressed into a metal shell moving through a vacuum at a fraction of light speed. Every atom that enters a human body must eventually be recovered and reused. There is no atmosphere to vent waste into, no ocean to absorb runoff, no geological cycle to lock away carbon and release oxygen. Every chemical cycle that Earth performs effortlessly across millions of square kilometers of biosphere must be replicated deliberately, artificially, and reliably across a closed system measured in square kilometers at most. The biological challenges alone are extraordinary. Earth's ecosystems are not simple machines. They are staggeringly complex webs of interdependence, built over billions of years of co-evolution. The soil beneath your feet contains more microbial species in a single tablespoon than there are stars in the Milky Way. Those microbes, bacteria, archaea, fungi, protists, perform functions essential to plant growth, nutrient cycling, waste decomposition, and atmospheric chemistry that we understand only partially, even after decades of intensive study. A generation ship attempting to replicate a closed food-producing ecosystem must either carry that microbial complexity in full, which means carrying billions of species of organisms that interact in ways we cannot fully predict or control, or find engineered substitutes for every biological function those organisms perform. Neither option is simple. Neither option is fully within our current capability. Biosphere 2, the closed ecological experiment conducted in Oracle, Arizona, in the early 1990s, offers a sobering case study. The facility was designed as a fully sealed, self-sustaining biosphere of roughly 1.27 hectares, housing 8 researchers for 2 years in conditions intended to simulate a self-contained life support system. The results were illuminating precisely because of how many things went wrong. Oxygen levels dropped unexpectedly as soil microorganisms consumed it faster than plants could replenish it, eventually requiring the injection of outside oxygen to prevent a medical emergency. Certain animal species went extinct while others overpopulated. Crop yields were insufficient. requiring the crew to operate on reduced calorie intake. Trace gas levels shifted in unexpected ways. The lesson of Biosphere 2 is not that closed ecological systems are impossible. It is that they are profoundly more complex than any engineering plan can fully anticipate in advance. And a generation ship, unlike Biosphere 2, cannot crack open a hatch and let in outside air when the oxygen drops. But let's go deeper than the biology, because the biological challenges, significant as they are, may actually be the more tractable part of the generation ship problem. The deeper challenge is social, psychological, civilizational. What happens to a human community when it is closed, isolated, and finite, not for a few months or a few years, but for generations? What does it mean to be born into a world with hard walls? To grow up knowing that you will never stand on a planet? To live your entire life inside a machine, moving toward a destination you will never reach, chosen by ancestors you have never met? These are not abstract philosophical questions. They are practical concerns with real consequences for mission success. Because a generation ship does not arrive at its destination with its cargo intact if the social fabric of the community aboard tears apart at some point during the journey. And the history of isolated human communities, on islands, in mountain valleys, in closed religious communes, in long-duration Antarctic stations, suggests that social cohesion under conditions of enforced isolation is not guaranteed. It is fragile. It requires active, intentional maintenance. It requires governance structures that are legitimate and adaptable. It requires a sense of shared purpose that can survive being transmitted across generations to people who had no choice in the matter. That last point is perhaps the most ethically and philosophically challenging aspect of the generation ship concept. The founding generation, the people who step aboard and choose to make the journey, do so voluntarily. They understand what they are committing to, at least in principle. But the children born aboard the ship did not choose this. They were born into a situation not of their making, aboard a vessel with no exit, heading toward a destination they played no part in selecting, carrying a mission defined by people who lived and died before them. Is that ethical? Does a generation have the right to make that choice for all the generations that follow? These are questions that philosophers, ethicists, and legal scholars have begun to take seriously in the context of serious interstellar mission planning, not because we are about to launch a generation ship, but because thinking carefully about these questions now is part of what it means to approach the project of interstellar travel with the seriousness it deserves. Geneticists have added another layer of complexity to the generation ship conversation that tends to get less public attention but is just as significant. It has to do with the minimum viable population, the smallest number of genetically diverse individuals needed to sustain a healthy human population across multiple generations without accumulating the harmful effects of inbreeding. Population genetics tells us that small, closed populations are vulnerable to what biologists call a founder effect, the loss of genetic diversity that occurs when a large population is reduced to a small founding group. The descendants of that founding group carry only the genetic variation present in the founders. Rare but beneficial genetic variants that existed in the broader population may be lost entirely. Meanwhile, any harmful recessive alleles that happen to be present in the founders have a much higher probability of appearing in their expression in later generations, as related individuals are more likely to share those alleles and pass them in combination to their children. The question of how many people a generation ship must carry to avoid these genetic bottleneck effects has been studied seriously by researchers including Cameron Smith at Portland State University, who published detailed analyses of minimum viable interstellar population sizes. His work suggests that a truly genetically healthy founding population, one that maintains sufficient diversity to avoid inbreeding depression across a multi-generational journey, would need to be in the range of somewhere between 14,000 and 40,000 individuals, not the small crew of a few dozen that early science fiction imagined, tens of thousands of people, which means a vessel of truly extraordinary size and complexity, a city, not a ship, a mobile civilization, not a transport, and even with those numbers, random genetic drift, the statistical fluctuation of allele frequencies in finite populations would inevitably reduce genetic diversity over multiple generations. Some researchers have proposed supplementing the founding population's genetics with frozen genetic material, sperm, eggs, or embryos that could be introduced into later generations to refresh the gene pool. This is technically feasible with current or near-future biotechnology, but it introduces social and ethical dimensions of its own, designer genetics for an entire civilization, managed by whoever controls the stored material. Who makes those decisions? What values guide them? How does a community many generations into a journey feel about the fact that their genetic heritage is being managed by a plan laid down by their ancestors? There is a concept in the generation ship literature that I find genuinely one of the most thought-provoking ideas in all of space exploration. And it comes not from an engineer or a physicist, but from a sociologist. It is called the problem of the middle generations. And it goes like this: the founding generation, the ones who left Earth, have a clear, visceral connection to the mission. They remember Earth. They chose this. They carry within themselves the living memory of why they are doing what they are doing. The arrival generation, the descendants who actually reach the destination star, have an equally clear connection to the mission's purpose. They are the ones who will step out of the ship, breathe new air, stand on new ground, and fulfill everything their ancestors set in motion. They have a destination, they have a moment of completion, they have the payoff. But the middle generations, the people who live and die somewhere in the middle of the journey, generations removed from Earth's memory, but equally far from the destination's reality. What anchors them? They did not choose this journey. They will not see its end. They are living in the middle of someone else's story, on a ship that is always between places, never arriving, never departing. For them, the ship is not a means of getting somewhere. The ship is simply the world, the only world, and the mission that gives meaning to the journey is, for them, purely abstract. A story told by elders, a destination described in documents, a purpose inherited rather than chosen. The sociological research on purpose and meaning in communities is unambiguous about what happens when shared purpose becomes abstract and inherited rather than lived and chosen. Communities fragment. Subgroups form with their own competing narratives about what matters and why. Authority structures that made sense in the founding context become contested in later contexts. Traditions calcify or are rejected. The mission, if it is not actively renewed and reinterpreted by each new generation in terms that resonate with their own lived experience, can fade from a living purpose into a dead doctrine. Managing this across multiple generations in a closed system with no exit is perhaps the deepest challenge the generation ship concept presents, and the solutions that have been proposed are as varied as the people proposing them, from elaborate governance constitutions designed to evolve with the community, to educational systems built around experiential understanding rather than rote transmission, to the deliberate cultivation of ritual and ceremony that keeps the mission's meaning alive as a felt reality rather than a remembered fact. Now let's look at this from a direction that I think is the most surprising and the most beautiful, because there is another version of the generation ship idea, one that reframes the entire concept in a way that dissolves some of its most troubling ethical dimensions. And it starts with a different question. Instead of asking, How do we get people from Earth to another star? It asks, what if the journey itself is not a sacrifice? What if it is the best possible life? What if a generation ship were not a vessel of deprivation, of confinement, of inherited obligation, but a genuinely extraordinary place to live? A world with its own landscapes, its own weather systems, its own ecology, its own culture, its own art, its own science. What if the people aboard were not passengers enduring a crossing, but inhabitants celebrating a civilization? What if the ship were large enough, and the engineering has been done on this, in concepts like the O'Neill cylinder, proposed by physicist Gerard O'Neill in the 1970s, to contain rotating sections generating artificial gravity, rivers, forests, open skies, communities of tens of thousands living in a biosphere rich enough to sustain genuine human flourishing? An O'Neill cylinder in its classic design is a rotating cylindrical habitat, several kilometers in diameter and perhaps 30 or more kilometers long, with an interior surface that serves as the living area. Rotation provides centrifugal force that mimics gravity. The interior could support agriculture, forests, water bodies, diverse ecosystems, cities. It would be, in its own right, a world, not a simulation of Earth, but a new world with its own character, its own microclimate, its own relationship between its inhabitants and their environment. The people living there would not be prisoners of a tin can crossing the void. They would be citizens of a civilization that happens to be moving. In that framing, the ethical problem of the middle generations shifts considerably. Yes, they did not choose to be born on this vessel. But did you choose to be born on Earth? Did you choose your country, your language, your culture, your historical moment? No human being chooses the world they are born into. What matters is whether the world they are born into is one that allows them to live well, to love, to grow, to create meaning, to contribute to something larger than themselves. A well-designed generation ship, a true O'Neill world in motion, might offer all of those things as fully as any civilization on the surface of a planet, not despite the journey, because of it. There is a concept in anthropology called the ethnosphere, the sum total of all human cultures, languages, beliefs, mythologies, and ways of knowing that exist on Earth. It is, in a sense, humanity's collective inner world, the vast interwoven tapestry of meaning that our species has woven over hundreds of thousands of years. A generation ship moving through interstellar space over centuries would develop its own contribution to the ethnosphere, a culture shaped by the experience of the void, a mythology built around stars and distance and the memory of a home world fading in the rear view, an art form that has never existed on Earth because no one on Earth has ever lived this life. The generation ship civilization would remember Earth, at first through the direct memories of founders, then through stories, then through documents and recordings, and eventually through the half-mythologized narrative that all founding moments become over sufficient time. Earth would be, for later generations, what our distant ancestors' African homeland is to most modern humans, a point of origin held in cultural memory, real in its influence on identity, but no longer accessible in experience. A place that shaped everything about who they are without being a place any of them have ever stood, and the destination, the new star system, the new planets, the new world waiting at the end of the journey, would take on a mythological weight of its own, not just a place to land, a promised world, the fulfillment of a covenant made generations ago by ancestors who stepped aboard a ship and pointed it at a star. The moment of arrival, whenever it came, for whichever generation was alive to experience it, would be one of the most extraordinary moments in the history of the human species, a moment that would be remembered and told and retold for as long as human civilization continued to exist. Before we leave the generation ship behind, I want to bring in something from modern genetics that adds an entirely new dimension to this conversation. because recent research has revealed something about the human genome that changes the calculus of long-duration space habitation in a way that nobody fully anticipated. It has to do with telomeres and with what space does to them. Telomeres are the protective caps at the ends of chromosomes, repetitive sequences of DNA that protect the chromosome from degradation during cell division, similar to the plastic tips on the ends of shoelaces. Every time a cell divides, telomeres shorten slightly. When they become too short, the cell can no longer divide safely and enters a state called senescence, or it triggers its own death. Telomere length is, in a rough sense, a biological clock, a measure of how many more divisions a cell has left, and it is associated with aging, with cancer risk, and with a range of age-related diseases. NASA's twin study, one of the most comprehensive human spaceflight studies ever conducted, comparing astronaut Scott Kelly, who spent 340 consecutive days aboard the International Space Station, with his identical twin brother Mark, who remained on Earth, found something surprising. Scott's telomeres actually lengthened during his time in space, then rapidly shortened again after his return to Earth, eventually settling at lengths shorter than before the mission. The mechanisms behind this are not yet fully understood, but it suggests that the space environment, the radiation exposure, the microgravity, the altered metabolic demands, interacts with fundamental cellular aging processes in ways that are complex, bidirectional, and not yet predictable over the timescale of a generation-long journey. For a community living aboard a generation ship for a century or more, those interactions, played out across thousands of individuals, across multiple generations of cellular and genetic inheritance, could produce biological outcomes that we simply cannot anticipate with our current understanding. Evolution does not stop on a generation ship. Natural selection continues to operate wherever organisms reproduce differentially. Over generations, the population aboard might begin to diverge biologically from the population that remained on Earth, adapting to the specific pressures of their environment in ways both guided and unguided by the choices of the community and its designers. Arrive at a new star system after 200 years, and the people stepping out might be, in subtle but real ways, already slightly different from the humans who stepped in. That thought, the idea of a humanity that diversifies as it spreads across the cosmos, each branch shaped by its own unique journey, brings us to something that I want to sit with for just a moment before we move forward, because it represents, in the most literal possible sense, the continuation of the oldest story in the history of life on Earth. Life moves, life spreads, life fills available niches and adapts to new environments and diversifies in ways that produce, over sufficient time, forms and capabilities that were not present at the beginning, from the first cells in ancient oceans to the vast proliferation of species that fills every corner of this planet today. Life has always been on a journey, always reaching into new territory, always becoming something slightly different than it was before in response to the demands of new environments. We are not separate from that process. We are its current leading edge. And the generation ship, the idea of carrying life deliberately, intentionally, purposefully across the gulf between stars, is perhaps the most conscious, the most deliberate, the most human expression of something that life has been doing, unconsciously and relentlessly, for 4 billion years. We are the universe's way of spreading life across itself. And 1 light year is where that story, quite possibly, begins. Let's come back to Earth, not as a retreat from everything we have been exploring, but because what is happening right now, today, in the laboratories and observatories and mission control rooms of our world, is more relevant to this journey than most people realize. We have spent 8 parts of this video looking outward at the physics of relativistic travel, at the biological and psychological realities of deep space, at the cosmic scale that makes one light-year feel simultaneously enormous and trivial, at the engineering challenges that stand between our ambitions and the stars. Now I want to look at the present moment, because the present moment in space exploration is quietly and without enough fanfare one of the most extraordinary periods in the history of our species' relationship with the cosmos. And it starts with something that was not possible just a few decades ago, something so fundamental to the question of why we would ever want to travel one light year in the first place that its absence used to be one of the most significant gaps in all of astronomy. For most of human history, we did not know whether other stars had planets. We suspected it, we hoped for it, we built philosophical arguments in favor of it going back to ancient Greece, where thinkers like Epicurus proposed that the universe must contain countless worlds. But we did not know, we had no data, we had no confirmed detection. The question of whether the Sun was unique in hosting a planetary system, or whether planets were a common feature of stars throughout the galaxy, was genuinely, frustratingly open until the final decade of the 20th century. In 1992, Polish-American astronomer Alexander Wolszczan and Canadian astronomer Dale Frail announced the detection of the first confirmed planet outside our solar system, orbiting not a sun-like star, but a pulsar. A pulsar is the rapidly rotating, ultra-dense remnant left behind when a massive star explodes as a supernova. The fact that planets could exist even around the violent, radiation-blasting remnant of a stellar explosion was itself extraordinary. It suggested that planet formation was a robust, resilient process capable of occurring in environments far more hostile than our own solar system. 3 years later, in 1995, Swiss astronomers Michel Mayor and Didier Queloz announced the first confirmed planet orbiting a Sun-like star, 51 Pegasi b, a gas giant roughly half the mass of Jupiter, orbiting its host star at a fraction of the distance between Mercury and our Sun, completing one orbit every 4.23 days. That discovery earned Mayor and Queloz the Nobel Prize in Physics in 2019. It cracked the door to the universe of other worlds wide open. What followed was a flood, a torrent, a revolution in our understanding of the galaxy that is still accelerating. NASA's Kepler Space Telescope, launched in 2009 and operating until 2018, monitored the brightness of roughly 150,000 stars simultaneously, watching for the tiny, periodic dimming caused when a planet passed in front of its host star, a technique called the transit method. In 9 years of operation, Kepler confirmed the existence of more than 2,700 exoplanets and identified thousands more candidates awaiting confirmation. What it revealed changed everything. Planets are not rare, planets are not exceptional, planets are the default. The galaxy is overwhelmingly, almost incomprehensibly full of them. Statistical analyses based on Kepler's data suggest that there are, on average, more than one planet for every star in the Milky Way. With somewhere between 200 billion and 400 billion stars in our galaxy, that means a comparable number of planets, and likely more, since many stars host multiple planetary systems, and within that enormous population of worlds, a significant fraction orbit within the habitable zones of their host stars. The temperature ranges where liquid water could exist on a planetary surface. Estimates suggest that there could be tens of billions of potentially habitable rocky worlds in the Milky Way alone, tens of billions in one galaxy, among 2 trillion galaxies in the observable universe. Kepler's successor, the Transiting Exoplanet Survey satellite, known as TESS, launched in April 2018 and has been systematically scanning nearly the entire sky, monitoring hundreds of thousands of stars for transiting planets. TESS is particularly focused on finding planets around nearby stars, the ones close enough to Earth that follow-up observations with more powerful instruments are feasible. As of the mid-2020s, TESS had confirmed hundreds of new exoplanets and generated thousands of additional candidates. It is, in a real sense, drawing the map of the solar neighborhood, cataloguing the worlds within reach of future observation and, in the very long term, future visitation. But planet detection is only the beginning of what current and near-future astronomy can do. The next frontier, the one that the entire exoplanet science community is building toward with almost electric excitement, is atmospheric characterization. Not just knowing that a planet exists, not just measuring its size and orbit, but actually analyzing the chemical composition of its atmosphere. Detecting the specific molecules present in the air of a world 20, 30, 50 light years away, looking for water vapor, carbon dioxide, methane, oxygen, ozone, the specific chemical fingerprints that on Earth are produced and maintained by the presence of living organisms, what scientists call biosignatures. The James Webb Space Telescope, launched on the 25th of December 2021, after decades of development and a series of delays that tested the patience of an entire generation of astronomers, is the most powerful space telescope ever deployed, and atmospheric characterization of exoplanets is among its most eagerly anticipated science goals. Webb observes primarily in infrared light, which is ideal for detecting the thermal emission and transmission spectra of planetary atmospheres. When a planet passes in front of its host star, a tiny fraction of starlight filters through the planet's atmosphere before reaching our telescopes. Different molecules absorb different wavelengths of that light, leaving characteristic dips in the spectrum, a chemical fingerprint readable across light years of space. Early Webb results have already demonstrated this capability in remarkable ways. In 2022, Webb detected carbon dioxide in the atmosphere of the hot gas giant WASP-39b, the first unambiguous detection of carbon dioxide in an exoplanet atmosphere, as a demonstration of the telescope's extraordinary sensitivity. Subsequent observations have continued to push the boundaries of what atmospheric characterization can achieve. The telescope is now turning its attention to smaller, rockier worlds, including planets in the TRAPPIST-1 system, a remarkable collection of 7 Earth-sized planets orbiting a cool red dwarf star just 39.6 light-years from Earth, at least 3 of which orbit within the star's habitable zone. TRAPPIST-1 deserves its own moment here because it is one of the most extraordinary discoveries in the history of exoplanet science, and one of the most tantalizing targets for the search for life beyond Earth. The system was first characterized in detail by a team led by Belgian astronomer Michael Gillon, using the TRAPPIST telescope in Chile, whose name gave the system its designation, with results published in the journal Nature in 2017. 7 rocky, Earth-sized planets, all within a zone closer to their star than Mercury is to our Sun, orbiting a red dwarf star so cool and dim that it glows more orange-red than yellow-white. 3 of those 7 worlds, designated TRAPPIST-1 and G, sit within the habitable zone. Some models suggest they could harbor liquid water. Some models suggest they could have atmospheres. Whether any of them actually do, whether any of them host conditions even remotely hospitable to chemistry complex enough to produce life, is precisely what Webb is working to determine. The early results are genuinely intriguing and frustratingly ambiguous, which is exactly what science at the frontier of knowledge usually looks like. Some observations suggest that at least one of the inner planets may lack a substantial atmosphere. Others leave open the possibility of atmospheric presence on the outer habitable zone worlds. The story is still being written, the data is still coming in, and the scientific community is watching with a level of collective attention and anticipation that has not been matched since the first moon landings. At 39.6 light-years away, TRAPPIST-1 is beyond the range of any technology we could build today or in the foreseeable future for a crewed mission, but it sits within the range of future astronomical instruments capable of imaging its planets directly, of actually taking pictures, however low resolution, of individual worlds in that system. The Habitable Worlds Observatory, currently in the planning stages as a potential NASA flagship mission for the 2030s and beyond, is specifically designed with the capability to directly image Earth-sized planets in the habitable zones of nearby Sun-like stars, to take, for the first time in history, a photograph of another Earth. Not a data point, not a spectrum, a picture. Now let me bring something into this conversation that I think is one of the most quietly revolutionary developments in space exploration, one that rarely gets the mainstream attention it deserves, but that is steadily, methodically transforming our capability to actually reach beyond the Earth-Moon system and eventually, perhaps, beyond the solar system entirely. It is the rise of what engineers call in-space propulsion development. For most of the history of spaceflight, rockets have worked by carrying both their fuel and their oxidizer, the substance needed to make the fuel burn, aboard the vehicle from launch. This is extraordinarily inefficient by mass. The Tsiolkovsky rocket equation, derived by that same Russian pioneer Tsiolkovsky, who first imagined generation ships, describes the fundamental relationship between a rocket's exhaust velocity, its mass ratio of fuel to vehicle, and the velocity change it can achieve. And what the equation reveals is unforgiving. To achieve very high velocities using chemical rockets, you need an almost ridiculous ratio of fuel mass to payload mass. The Saturn V rocket that sent humans to the Moon was, at launch, roughly 85% propellant by mass. The actual payload, the capsule, the lunar module, the astronauts, was a tiny fraction of the total. Electric propulsion systems, ion drives, Hall effect thrusters and related technologies offer a completely different trade-off. Instead of burning chemical fuel to produce thrust, they use electric power to accelerate ions, charged particles, to very high exhaust velocities, producing thrust far more efficiently than any chemical rocket, though at much lower thrust levels. NASA's Dawn spacecraft, which visited the asteroid Vesta and the dwarf planet Ceres, was powered by ion propulsion. The Hayabusa missions by the Japan Aerospace Exploration Agency, which collected samples from 2 different asteroids and returned them to Earth, used ion drives. The technology is not theoretical, it is operational, flight-proven, and steadily improving. The next generation of electric propulsion systems, including advanced Hall thrusters being developed by NASA, by private companies, and by space agencies in Europe, Japan, and elsewhere, aims to achieve higher thrust levels while maintaining the exceptional efficiency that makes electric propulsion so attractive for deep space missions. Paired with nuclear power sources, either radioisotope thermoelectric generators, which convert the heat from radioactive decay into electricity, or full nuclear fission reactors, which could provide power levels orders of magnitude higher, advanced electric propulsion could enable missions to the outer solar system and beyond on timescales that are dramatically shorter than those achievable with chemical rockets. NASA's Nuclear Thermal Propulsion Program, actively under development and receiving sustained funding, aims to demonstrate a nuclear thermal rocket engine that could be tested in space within this decade. A nuclear thermal rocket does not generate electricity and then use it to accelerate ions. It passes liquid hydrogen propellant through the core of a nuclear fission reactor, heating it to temperatures far beyond what any chemical combustion can achieve, and expelling it at high velocity for thrust. The specific impulse, the efficiency metric for rocket engines, of a nuclear thermal rocket is roughly twice that of the best chemical rockets, not as efficient as an ion drive, but with far higher thrust levels, making it suitable for crewed missions that need to reach high velocities relatively quickly. There is something happening on a completely different scale that I want to make sure we include here, because it represents perhaps the most ambitious concrete step toward interstellar travel that has ever moved from pure concept into actual funded development. Breakthrough Starshot, which we mentioned briefly, is worth returning to in more detail because the engineering being done under its umbrella is genuinely extraordinary, and the mission architecture it proposes, however far from completion, represents a real physics-grounded path to sending an artifact of human creation to another star within a human lifetime. The core concept is deceptively simple. Instead of building a large spacecraft and trying to power it to interstellar velocities, you build the smallest possible functional probe, essentially a gram-scale chip carrying a camera, a communications laser, and basic navigation electronics attached to a sail made of an ultra-thin, highly reflective material, and you accelerate it using a ground-based laser array of extraordinary power. The laser pushes on the sail the way wind pushes on a boat's sail, but using photon pressure rather than air pressure. The advantage of laser propulsion is that the energy source stays behind on Earth. You do not need to carry fuel, which eliminates the most crushing constraint of conventional rocketry. The disadvantage is that you need a truly enormous, precisely coordinated array of lasers. The Breakthrough Starshot baseline design calls for a total power of roughly 100 gigawatts delivered to the sail over a period of a few minutes to accelerate the chip to roughly 20% of light speed, 100 gigawatts. For reference, the entire electrical generating capacity of the United Kingdom is currently around 80 gigawatts. The engineering challenges of building a coherently phased laser array capable of delivering that power to a tiny, rapidly accelerating target are formidable. The materials science challenge of building a sail that can absorb and reflect that much laser energy without being destroyed is formidable. The challenge of keeping the chip on target as it accelerates is formidable. Every one of these challenges is being actively researched. Solutions are being proposed, tested in small-scale experiments, refined. The project is not in standby mode. It is in active scientific and engineering development. If it succeeds, not tomorrow, not next decade, but within the coming generations of technological development, a Starshot chip could reach Alpha Centauri in roughly 20 years. It would fly through the system, unable to decelerate, snapping images and collecting data for a few hours of closest approach, then transmitting that data back to Earth at the speed light travels, a journey of 4.24 years. The first close-up images of another star system, the first data from another solar system, the first confirmation or denial of what Proxima Centauri b actually looks like up close. Within a human lifetime, that is not science fiction. That is an engineering project with a budget and a team and publications in peer-reviewed journals. Let me bring in one more thread of current science that I think changes the emotional register of this entire conversation. Because all of the technology, all of the mission architecture, all of the physics we have discussed, it ultimately serves a question. The question, the one that has been implicit in every part of this video, lurking beneath every discussion of radiation and time dilation and generation ships and laser sails, the question that our species has been asking in one form or another since the first human being lay on their back in the dark and looked up at the stars and felt the stirring of something they could not name. Are we alone? Astrobiology, the scientific study of the origin, evolution, and distribution of life in the universe, has matured enormously as a discipline over the past 3 decades. What was once considered a fringe interest, tolerated on the edges of respectable science, is now a central focus of NASA, the European Space Agency, and space agencies around the world. the discovery that life on Earth exists in environments once considered completely uninhabitable, in boiling acidic volcanic vents, in the crushing darkness of the deep ocean floor, in hypersaline lakes, in Antarctic ice, in the radiation-drenched rocks of the upper atmosphere, has dramatically expanded our sense of what conditions life can tolerate. These organisms, called extremophiles, suggest that life is not fragile, it is tenacious, it is creative, it finds ways, and if life is that robust here, the question of whether it has found ways elsewhere becomes not just plausible but, to many researchers, genuinely probable. The detection of phosphine in the atmosphere of Venus, announced in 2020, though subsequently subject to significant scientific debate about the reliability of the detection, briefly electrified the scientific community with the possibility of atmospheric chemistry in Venus's cloud layers that might, under very specific conditions, be associated with biological processes. The debate over that detection is ongoing and unresolved, but it illustrated something important. The instruments, the techniques, and the conceptual frameworks for detecting signs of life across interplanetary and eventually interstellar distances are being built right now. The machinery of discovery is being assembled. Mars remains one of the most compelling targets in our search for life, not for life on its surface today, which the radiation environment makes extremely unlikely, but for ancient life in its past, when Mars had liquid water on its surface, a thicker atmosphere, and potentially habitable conditions. NASA's Perseverance rover is at this moment caching carefully selected rock samples from the Jezero crater, a location identified as an ancient river delta where conditions for life were once present, for eventual return to Earth by a future sample return mission. Those samples, when they arrive in terrestrial laboratories, will be subjected to analyses of extraordinary sensitivity. The results could be among the most significant in human history. And Europa, one of Jupiter's large moons, covered by a global ocean of liquid water beneath a shell of ice, heated by the tidal flexing of Jupiter's immense gravity, and Enceladus, a moon of Saturn from which geysers of water vapor and organic molecules erupt into space from a similar subsurface ocean. Both represent environments where the basic ingredients for life as we understand it are present today, right now, in our own solar system. NASA's Europa Clipper mission, launched in October 2024, is currently en route to the Jovian system, where it will conduct dozens of close flybys of Europa beginning around 2030, analyzing its surface, its ice shell, its magnetic environment, and the material erupting from its interior. What it finds could reframe the entire question of life in the cosmos. We are, right now, in the middle of the transition. Not at the beginning. We have already left Earth, already reached the Moon, already sent emissaries to every planet in the solar system and beyond the heliosphere, but not yet at the point of interstellar travel, not yet at the point of confirmed life detection, not yet at the point where the question of whether we are alone has a definitive answer. We are in the middle, and the middle of a story is where everything matters most. It is where the choices are made that determine how it ends. It is where the curiosity, the investment, the courage to keep going despite the difficulty, where all of that either holds or falters. The generation doing this science right now, building these telescopes and launching these missions and developing these propulsion systems and asking these questions, this generation is writing some of the most consequential chapters in the history of human civilization. And every person who understands what is at stake, who cares about the answers to these questions, who supports the science and the exploration and the relentless, beautiful human refusal to stop asking why, every one of those people is part of it. You are part of it, not as a passive audience, as a participant in the civilization that is doing this. The civilization that looked at the night sky and decided that looking was not enough. That built instruments to see further. That sent machines to touch what eyes could never reach. That is now, seriously, with real funding and real physics and real engineering, beginning to think about how to reach the stars. 1 light year is where the next chapter starts, and the people who will write it are alive right now. We have come a long way together. Across 9 parts of this journey, we have moved through the interstellar medium, that vast, thin ocean of gas and dust and cosmic radiation that fills the space between stars. We have felt time bend around us as velocity climbs toward the cosmic speed limit. We have watched our bodies adapt and struggle in the absence of gravity, in the presence of radiation, in the silence of a darkness so complete it has no equivalent on Earth. We have seen the universe reveal itself in colors and shapes that human eyes were never designed to perceive. The blue compression of stars ahead, the red emptiness behind, the entire sky warped by the mathematics of motion into something alien and magnificent. We have grappled with the psychological transformation of deep isolation, with the overview effect that reshapes the self when Earth becomes a memory rather than a home. We have built in our imagination the vessels that might carry us there, the generation ships, the laser sails, the nuclear engines, and wrestled honestly with the challenges that make each of them extraordinary and difficult and real. We have looked at what science is doing right now, today, to narrow the distance between where we are and where this journey begins. And now, in this final part, I want to do something different. I want to step back from the physics, not abandon it. Everything we have discussed is grounded in real science, and I would not have it any other way. But I want to look at the whole picture. I want to ask the question that sits beneath all the other questions, the one that the physics alone cannot answer. Not just what would happen if you traveled 1 light year, but why? Why would anyone do this? Why does this question matter? What does the human drive to reach beyond everything familiar say about the kind of creature we are? And what might it say about the kind of future we are capable of building? Let's start with a fact that I find genuinely humbling every time I sit with it. Every human being who has ever lived, every person whose name history remembers, and every person whose name it does not, was born, lived, and died within an extraordinarily thin shell of atmosphere wrapped around a single rocky planet, orbiting an unremarkable star in the outer arm of a barred spiral galaxy among 2 trillion galaxies in the observable universe. Every war was fought here, every love story unfolded here, every work of art was created here, every scientific discovery was made by minds that grew up breathing this specific mix of nitrogen and oxygen, under this specific strength of gravity, illuminated by this specific star. All of human experience in its entirety has occurred within a volume of space so vanishingly small compared to the cosmos that representing it accurately on any map of the universe would require a dot smaller than any printing technology can produce. 1 light year is 9.46 trillion kilometers. The distance from the surface of the Earth to the edge of our atmosphere, the boundary of the biosphere that has contained every human life in history, is roughly 100 kilometers. 100 kilometers versus 9.46 trillion. That ratio is not a fact to be absorbed quickly and moved past. It is something to sit with, something to let settle into your understanding of your own situation. You are not, as it might feel from the inside, at the center of things. You are on the shore of an ocean so vast that the shore itself, the only place your species has ever stood, is invisible from any meaningful distance. That is not a discouraging thought. I want to be clear about that. It is one of the most energizing thoughts available to a human mind once the initial vertigo passes, because it means that what we have accomplished, all of human civilization, all of our science and art and philosophy and technology, built from scratch on one small world with no instruction manual and no outside help, we accomplished at the very beginning. at the very start of what we might become. The entirety of human achievement so far is the preface, the opening line, the first note of something that, if we are wise and bold and careful enough to survive our own adolescence as a civilization, could become something whose scope we cannot yet imagine. There is a framework in the study of civilizational development called the Kardashev Scale, proposed by Soviet astronomer Nikolai Kardashev in 1964. It classifies civilizations not by their technology or their culture, but by their energy use, because energy consumption, Kardashev argued, is the most fundamental measure of what a civilization is capable of doing. A Type 1 civilization harnesses all the energy available on its home planet, geothermal, wind, solar, tidal, the works, and uses it with complete efficiency. A Type 2 civilization harnesses all the energy output of its host star, an almost incomprehensible leap, but one that the physics permits through structures like the theoretical Dyson sphere, a shell or swarm of collectors surrounding a star to capture its full energy output. A Type 3 civilization harnesses the energy of an entire galaxy, accessing the output of hundreds of billions of stars. Where does humanity currently sit on this scale? We are, by Kardashev's original calculations, roughly a Type 0.7 civilization. We have not yet achieved even the lowest rung of his framework. We are pre-Type 1, still burning fossil fuels, still generating electricity at enormous inefficiency, still unable to prevent the waste of the majority of the energy we produce. The gap between where we are and even a Type 1 civilization is genuinely vast. The gap between Type 1 and Type 2 is almost beyond imagination. And yet, and this is the critical point, none of those transitions require new physics. None of them require the universe to behave differently than it already does. They require only ingenuity, time, and the survival of the civilization doing the growing. The physicist Michio Kaku has pointed out that the transition from Type 0 to Type 1, the transition our civilization is currently in the middle of, driven by the global spread of technology, communication, science, and increasing energy production, is the most dangerous transition of all. It is the point at which a civilization has developed the tools to destroy itself, nuclear weapons, biological engineering, environmental manipulation on a planetary scale, but has not yet developed the wisdom and the governance structures to reliably prevent that destruction. We are in that transition right now, and the outcome is genuinely uncertain. History does not guarantee our success. The cosmos does not owe us survival, whether we may get it through this period and emerge as a spacefaring, multiplanetary, eventually interstellar civilization, or whether we do not, depends on choices being made by people alive today. That is not meant to frighten you. It is meant to show you that the stakes of the question we have been exploring, the question of interstellar travel, of reaching the stars, are not abstract. They are immediate. They are present. Because a civilization that learns to think on interstellar timescales, that takes seriously the project of becoming a multi-world species, that invests in the science and the technology and the social structures needed to sustain itself across centuries, that civilization is, by the very act of thinking that way, more likely to navigate the near-term dangers. The long view and the immediate view are not in tension, they reinforce each other. The best reason to start thinking seriously about one light year is not that we are going there next year. It is that the civilizational maturity required to even seriously attempt, it is exactly the maturity we need to survive the next century. Let me tell you about something called the cosmic perspective. It is a phrase most closely associated with astrophysicist Neil deGrasse Tyson, but the concept is older and wider than any one person. It is the shift in understanding, in felt understanding, not just intellectual acknowledgement, that occurs when you genuinely internalize the scale of the universe and your place within it. Not just knowing the numbers, feeling them. letting them reshape the way you experience your own life and your own moment in history. The cosmic perspective does something interesting to the things that feel most urgent, most divisive, most intractable from the inside of ordinary human experience. The borders between nations, lines drawn in the minds of people, enforced by armies, defended by ideologies, become invisible from orbit. From 1 light year away, they are beyond the resolution of any instrument we have ever built or could conceivably build. The conflicts that fill our news cycles and consume our political energy, the disputes over resources, over territory, over identity, over who gets to tell which story about the past, all of them are happening on a single pale blue dot that, from the distance of even our closest stellar neighbor, would be invisible to the naked eye. Not diminished in the sense of being unimportant, the suffering of any human being is real and matters, but placed in a context that makes the possibility of resolution seem not just desirable but almost absurdly achievable, given what we actually have in common. Carl Sagan, who gave us the phrase "pale blue dot" in his famous reflection on the Voyager 1 image of Earth taken from beyond the orbit of Neptune in 1990, put it better than almost anyone. He wrote that the Earth is a very small stage in a vast cosmic arena, and that our planet is a lonely speck in the great enveloping cosmic dark, that in our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves, and that it is up to us. It has always been up to us. That thought has never left me, and I think it is the right place from which to approach the final stretch of everything we have been building toward in this video. Because Sagan was not being pessimistic when he wrote those words. He was being precise. He was doing what the best science always does, stripping away comfortable illusions and replacing them with something harder and truer, and ultimately more beautiful. The universe does not have a plan for us. There is no cosmic safety net, no backup civilization waiting to intervene if we make the wrong choices. No guarantee written into the laws of physics that intelligence, once it arises, gets to survive. We are, as far as we can currently determine, on our own, and on our own, we have to decide what kind of story this is going to be. The choice to reach for the stars is, at its core, a choice about what kind of story we want to tell. It is a choice to be the kind of civilization that looks at a distance of 9.46 trillion kilometers and says, "Not yet, but someday." It is a choice to invest in the long game, to care about what happens not just in this decade or this century, but in the millennia and the millions of years that follow, if we are fortunate and wise enough to have them. It is, in the deepest sense, a statement of faith, not religious faith, but something equally powerful. Faith in the future, faith in the capacity of human curiosity and human ingenuity to keep finding ways forward. Faith that the questions are worth asking even when the answers are centuries away. I want to bring in a concept here that physicists and philosophers of science sometimes call the Fermi paradox, because it adds a layer of urgency to everything we have discussed that I think deserves to be felt rather than just understood. The Fermi paradox, named for physicist Enrico Fermi, who reportedly posed the question during a casual lunch conversation at Los Alamos in 1950, is deceptively simple. Given the age of the universe, given the enormous number of stars and planets, given the robust and tenacious nature of life as we observe it on Earth, given the fact that even at sub-light speed interstellar travel speeds a sufficiently motivated civilization could colonize the entire Milky Way in somewhere between 1 million and 10 million years, a blink of an eye in cosmic terms, where is everybody? Where are the signals? Where are the megastructures? Where are the probes? Where are the transmissions? Where is any evidence whatsoever of any other technological civilization anywhere in the observable universe? We have been scanning the sky for deliberate radio signals since 1960 when astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars as part of Project Ozma, the first organized scientific search for extraterrestrial intelligence. In the decades since, the search has expanded enormously in scope, sensitivity, and the range of signal types being monitored. And across all of that searching, across more than 6 decades of increasingly sophisticated observation, the answer has been the same: silence. The sky is quiet in ways that are, when you think carefully about what we would expect given the age and size of the universe, genuinely strange. The Fermi paradox has generated dozens of proposed resolutions. Perhaps intelligent life is simply extremely rare, rarer than the numbers of planets suggest, because the transition from chemistry to biology, or from simple biology to complex multicellular life, or from complex life to technological civilization, involves one or more steps that are so improbable that they happen only once or a handful of times in a galaxy the age of ours. This is the rare Earth hypothesis, and it has serious scientific support. Perhaps civilizations reliably destroy themselves before they reach the capability for interstellar communication. The sobering possibility that the same technological development that enables a civilization to reach outward also reliably produces the tools of its own destruction, and that most civilizations do not survive that transition. This is sometimes called the Great Filter. And the deeply uncomfortable question it raises is whether the Great Filter lies behind us in our evolutionary history, or ahead of us in our future. Or perhaps, and this is the possibility I find simultaneously most hopeful and most humbling, the universe is simply so vast, and the timescales of civilizational development so long, and the physics of interstellar communication so demanding, that the silence is simply what we should expect at our current stage of development. Perhaps there are other civilizations out there. Perhaps the galaxy is, in fact, full of life, scattered across distances so enormous and separated by timescales so vast that the probability of any two civilizations existing close enough and simultaneously enough to detect each other is genuinely low, not because they are not there, but because the cosmos is so unimaginably large that even two very common things can be effectively invisible to each other across its scale. We do not know. That is the honest answer. We genuinely, truly do not know, and that uncertainty is not a failure of science. It is science doing exactly what science is supposed to do, holding open the space of the unknown with intellectual honesty rather than filling it prematurely with comfortable answers. The uncertainty is the invitation. It is the open door. It is the reason the question remains one of the most important questions our civilization has ever asked. Now I want to bring this back to the personal, to you specifically, because we have been talking about civilizations and timescales and Kardashev scales and Fermi paradoxes, big, sweeping, almost abstract ideas. And I do not want to lose what is most immediate and most real about this conversation, which is that you are a person, a human being made of roughly 37 trillion cells, each one the descendant of an unbroken chain of living organisms stretching back 3.8 billion years. You are the product of an evolutionary process so long and so improbable that the odds of your specific existence, your particular arrangement of atoms, your specific genome, your singular perspective on the universe, are so vanishingly small as to be effectively miraculous by any intuitive standard. You are, as Sagan also said, made of star stuff. The carbon in your body was forged in the cores of stars that lived and died before our sun was born. The iron in your blood was scattered across space by supernova explosions billions of years ago. You are not separate from the cosmos looking at it from the outside. You are the cosmos looking at itself, and what that means, what it really means, when you let it land, is that the curiosity you feel when you look up at the night sky is not incidental to the universe. It is the universe being curious about itself through you. The wonder you feel when you contemplate distances of 1 light year, or 4 light years, or the 200,000 light years across the Milky Way. That wonder is not a human quirk. It is something the universe has arranged through 4 billion years of biological evolution on one small rocky planet to be possible, to exist, to ask questions, to reach toward answers. You are not just an observer of the cosmic story. You are a character in it, a speaking part. One of the ways the universe has learned to know itself, that is not a small thing. That is, depending on how you look at it, the most extraordinary thing imaginable. Let me tell you what I think the real answer to our central question is. The question we started with 9 parts ago. What would really happen if you traveled 1 light year? The physics would happen. The time dilation would bend your experience of time in ways that separate you, mathematically and irrevocably, from the timeline of everyone you left behind. The radiation would challenge every biological defense your body has ever developed. The dust would test every material your engineers have ever devised. The darkness would press against your psychology in ways that training can prepare for but never fully simulate. The scale would do something to your sense of self that no amount of intellectual preparation can entirely anticipate. It would make you smaller in one sense and larger in another. Strip away the comfortable illusions of centrality and replace them with something harder and more honest, and eventually more freeing. The stars ahead would blue shift into fierce, compressed brilliance. The stars behind would redden and fade. The cosmic microwave background would pile up before you in a ring of cold light, the echo of creation itself, rendered visible by your velocity. You would fly through a medium that feels like vacuum, but is alive with hydrogen atoms and helium and carbon compounds and magnetic fields and cosmic rays, the breath of the galaxy, thin beyond imagination but real, physical, present. You would watch the solar system shrink behind you into a point of light, and then into nothing, and then into the memory of a point of light, and then into a story you tell yourself to remember where you came from. You would have time, more time than any human being in history has ever had to simply think, to sit with the largest questions, to feel, without distraction, the full weight of what it means to be alive and conscious in a universe of this scale. Some of that time would be terrifying. Some of it would be boring in ways that grind against every instinct you have. Some of it, the best of it, would be the most profound experience available to a human nervous system. The overview effect, extended not over minutes as astronauts experience it from orbit, but over months and years. The slow, sustained, cellular-level realization that the home you left is precious beyond any ordinary valuation, that the people on it matter in ways that distance makes luminous, that the pale blue dot is not small because it is insignificant, it is small because the universe is so large, and large does not mean better, and the smallness of Earth is precisely what makes the life on it so rare and so worth protecting and so worth returning to 1 light year, 9.46 trillion kilometers, the distance between our solar system and the first tentative edge of interstellar space that a future generation might dare to cross. It is not in cosmic terms very far at all. Proxima Centauri, our nearest stellar neighbor, sits at 4.24 light-years. The Milky Way stretches 100,000 light-years from edge to edge. The observable universe extends 46 billion light-years in every direction. 1 light-year is a beginning, the first step, the opening move in a game that, if our civilization survives and grows and keeps its curiosity alive, could eventually span the galaxy. But beginnings matter. First steps matter. The opening move sets the tone for everything that follows. And the fact that our civilization is, right now, in this decade, in this century, beginning to seriously ask how to take that first step, building the telescopes that map the destination, developing the propulsion systems that might one day provide the means, doing the biology and the psychology and the engineering that will eventually produce the knowledge needed to keep human beings alive and sane across the enormous distances involved. All of that is happening now. The story is being written now by scientists and engineers and mission planners and funding bodies, and yes, by the people who watch videos like this one and care enough about the question to spend time with it, to think about it, to share it, to let it change even slightly the way they see the sky. There is a tradition in science, not a formal one, not written into any curriculum, of ending the largest questions, not with answers but with better questions, because the best questions are the ones that open rather than close, the ones that, when you sit with them long enough, start to feel less like puzzles to be solved and more like doors to be walked through. And I want to close this video not with a summary of what we have learned. You have heard all of it, you have sat with all of it, you carry all of it now, but with a question. The question, the one that I think waits on the other side of everything we have discussed, not what would happen if you traveled 1 light year. But what happens to a species that decides to try? What does it become in the centuries and the millennia of preparation, of development, of failure and redesign and incremental progress, of generation after generation choosing to invest in a project whose payoff none of them will personally live to see? What does a civilization look like when it has genuinely internalized the long view? When it plans not for this election cycle or this fiscal quarter, but for this century and this millennium? What kind of science does it do? What kind of art does it make? What kind of politics does it practice? What kind of relationship does it have with the one small, beautiful, irreplaceable world that gave it life and that it must not destroy in its eagerness to reach beyond it? I think the answer, and I genuinely believe this, is that a civilization serious enough to reach for the stars is, almost by definition, a civilization that has learned to take care of the world it already has. Because the same long-term thinking that says we should invest in interstellar propulsion research for payoffs a century away also says we should invest in ecosystem preservation for payoffs a century away. The same scientific culture that demands rigorous honesty about the engineering challenges of a generation ship also demands rigorous honesty about the data on climate change, on biodiversity loss, on the health of the oceans and the atmosphere. The same humility required to look at 1 light year and say, we are not ready yet, but we will be, is the same humility required to look at our own civilization and say, we are not perfect yet, but we can be better. Reaching for the stars and taking care of the earth are not competing priorities. They are the same priority, viewed from different distances. They are both expressions of the same fundamental commitment to the survival and flourishing of the extraordinary, improbable, unprecedented thing that life on this planet has produced, to the continuation of the story, to the idea that the universe is better with us in it, asking questions, building things, making art, loving each other, and looking up the next time you step outside on a clear night and look up at the stars. And I hope you do this soon, and I hope you do it without your phone in your hand, without anywhere else to be, just you and the sky, and whatever time you can give it. I want you to try something, pick a star, any star, something bright, something that catches your eye, and hold in your mind, just for a moment, the distance, not as a number, as a physical reality. The light entering your eye right now left that star years ago, decades, centuries. It has been traveling through the interstellar medium, through that thin ocean of hydrogen and helium and cosmic rays and magnetic fields, for longer than some human civilizations have existed. It crossed 9, 40, 100 light years of absolute darkness to land, finally on your retina, on you, specifically, and somewhere along the path of that light, at a distance of 1 light year, which is where our story began, there is a boundary, Not a physical boundary, not a wall or a marker or anything you could see, but a conceptual one. The place where the sun's influence fades to the point where the interstellar medium truly takes over, where our solar system ends and the galaxy begins. Where the journey that defines the next chapter of our civilization's story starts. It is not unreachably far. It is not forbidden. The physics permits it. The ingenuity that has taken us from fire to fusion in 100,000 years is more than equal to it, given time. The question was never whether we could. The question is whether we will choose to. Whether we will be the generation or the sequence of generations that makes the choices and does the work and keeps the faith across the long, difficult, magnificent project of becoming a spacefaring species. I think we will. Not because I am naive about the difficulties. You have spent 10 parts of this video watching me lay out exactly how difficult it is. But because I have seen what human curiosity looks like when it is pointed at the cosmos. I have watched the images come back from Webb, from Perseverance, from Voyager, from Hubble, from every instrument we have ever pointed at the sky. I have read the papers and the proposals and the engineering studies produced by people who spend their careers thinking seriously about how to cross the interstellar void. And in all of it, in every equation and every design document and every photograph of a distant world, I see the same thing that has driven this species forward since the first human being looked at the horizon and wondered what was beyond it. We want to know. We cannot help wanting to know. It is, perhaps, the most essentially human thing about us, and 1 light year is where that wanting, finally seriously, for the first time in our history, starts to have a real answer. And if this blew your mind, you are not done yet. Click the video on your screen right now to explore how long it would really take to travel 1 light year. The answer is going to shock you far more than you expect. Trust me, you want to see this one.